that is the second session on robotics for agriculture. And in particular, this second session will be dominated by the subject of drones. The first will be drones plus other stuff, and the next two will mostly focus about drone technology. That is one of the... It's little technical problems, so we will have this session in which we will have 3 talks that will touch a lot concerning drones. So let me also welcome all the people that are following us from remote, both on Teams and on the YouTube channel. And I'm very pleased to start presenting our first speaker, that is Fabrizio Dabbene from the CNR in Torino. So Professor Dabbene is, first of all, a dear friend. We know each other since a long time, and is a very well-known person in the Control System Society in the world, and in particular is also the president of the Italian chapter of the IEEE Control System Society. He has a long career and a large range of interest that goes from theoretical aspects of control to applied ones. And I will not go on because it's always a little bit awkward when you're presenting someone that is a friend and has a very good curriculum, because then he will feel embarrassed, and I don't want to embarrass him for the fact that he is very good at what he does. So I'll just invite him on the podium and we'll ask him to tell us something.
So, Emanuele, thank you very much. It's nice when you start to have a long career, because it means that you're starting being not so young. But the nice thing of research, you always feel young. So thanks. I just want to start thanking the organizers of this BrIAS forum, and I'm very, very proud of being one of the BrIAS fellows. So thank you, Emanuele, and thanks all the BrIAS staff, and especially Anja. I think that nothing of this would happen without her. So the title of my talk today is Cooperation of Unmanned System for Agriculture 4.0. And I realized that I made 2 mistakes already in the title, so let me correct. The first one, I should use uncrewed, because I understand that unmanned is not gender neutral. And then Yael told me that now we are in agriculture 5.0. So I'm a little. So yes, I am indeed, my background is indeed in control. So it's a strange story why I've been working in these past 10 years, even more, 15 years on robotics and agriculture in general. And it is a story of friendship again, because my close friend and colleagues during the PhD, we were doing the PhD together in the same room. So you are young guys, you know that you start working together, talking together. After the PhD, we were looking for a job, and he found a job in the university in the agricultural department. And so we kept working together, and it came out that in the robotics and the agriculture department, they had problems which were very interesting from our point of view. And that really, we started working, and we keep working together, and we still work together because these are challenging problems. So before going to robotics, I want to tell you 2 stories of problems that we studied in the past, related more about food and food supply chain, because really you see that they are peculiar. There are some things about food that are very, very different from classical supply chain. So if you take this table and you put it in a warehouse because you have to sell it, you can keep it there for 1 month, 2 months, okay. You pay some fees, but then you take out the table and you sell it. If it is milk, or if it is a cow, I mean, okay, let's say an egg, it has an evolution. It's gonna go bad. Why? Because food is a dynamical system. It's a dynamical system that evolves by itself, and the evolution depends on where you store it. The temperature, the humidity, these kind of factors. And so really, we understood that you have to put these into the picture, and so treat this supply chain optimization as a hybrid system where you have dynamics. And we show how that you can take into account these dynamics, and you can solve a problem where you have this into account. And this, we won a Best Paper Award with this. I'm very proud because this was a nice work. Another work, also related to food, you have the classical traceability problem and the problem where you have failures. Let's say, we all are all aware that sometimes there are problems like, I remember the IKEA meatballs that had to retire a lot of meatballs because there were problems of contamination. So when you have that, with food, the problem is really that you start from the raw material. You have some processes which are mixing, which are storing, and you produce other things, like from flour and sugar, you can produce cakes. And then you have that the classical tracking or traceability problem is to know where the raw materials go. But when you have a failure, what you have to do is go back on the tree and see what are the materials involved and then go forward. And all these red things you have to retire because it may be contaminated. And so, really, you can try to formulate this problem in such a way. This is an optimization problem, so I was happy. Let's use our optimization knowledge to minimize, let's say, the worst case of the average number of materials that can be, that shall be taken out of the market if there are problems. And, okay, as Emanuele said, now I'm old, I wrote a lot of papers. This is my most cited paper. So my most cited paper is in agriculture. So let's get back to what is agriculture 4.5.0. So the nice and bad things of being at the second day is that you already heard this story many times, so you know what's happening. So the question is, we all know historically what happened for the Industrial Revolution. Were there something similar for the Agricultural Revolution? And, okay, this is really, let's say, an extreme view, but the extreme view of the Agricultural Revolution is what I call, what Paolo calls the tractor paradigm. So you build bigger tractors. So you have bigger fields, bigger tractors, autonomous tractors. This has been the problem. You have to increase production and increase production. I mean, so what is the problem? Is this something that is sustainable? This is going through some sustainable agriculture? I don't think so. And this is exactly the kind of answer that we saw in yesterday. So some of these pictures you saw. Some of the rovers you saw yesterday. So the idea, the modern, the 5.0 agriculture are systems which are autonomous, which have advanced sensing technologies, small systems that collaborate between each other. They are electrical and they are smart. So here I have the Tevel one, the field robotics one, and another one. There are many. This is the main idea. So, and the main idea, this is an important point, is that they should be, as much as possible, autonomous. So here I'm focusing on the fact that they should work by themselves, without remote, or at least minimizing the remote control part. So we had this project founded by the Italian government that we involved many universities in Italy, and which was indeed focused on new technical operative solution for the use of drone in agriculture 4.0. We work in vineyards. Why on vineyards? We are in Piedmont. I was born in Alba, Barolo, Barbera, Barbaresco. They're nice vineyards, and they have a lot of money, so they can invest. So this is one market. And so the idea is to have a collaboration of terrestrial and UAV robots. And what we have been proposing, looking also at the literature, is, first of all, we did a study of what are the different solutions for collaboration of robots. So you have peer-to-peer robotics, team robots, master-slave. And we sort of came up with this collaboration, which is a multi-phase collaboration. So different robots that act on the same field in different time. They collect information, and then you can use the information. So the idea is how, now they have to start the image again, to have an aerial robot that takes information on the map, builds a map. So that's what you do. If you want to travel around Brussels, first of all, you take a map of Brussels and decide how to navigate. But there's somebody that draws that map. And the map is simple. It's not just the photograph of Brussels. It's a map that gives you to go from there. So you have to collect the most simple information that you need. So to do that, the first work we did was sort of a work where we came out with a fully automatized system to go from a point cloud to what we called a simplified, low complex, simplified map. So you start with your point cloud, you automatically detect what is the canopy, what is the floor, and then you have algorithms to have a low complexity representation of this. Why low complexity? Because you try to extract only the information that you need to pass to the drone when it has to go through or over the canopies. Then we did some work, some applications. I mean, we try to show that our knowledge of control guides can improve the way drones move over terrain, always in the direction of going towards autonomous navigation. So, and precise. So to collect this point cloud, you need to be very precise. And so we used classical tools that Emanuele, many control guys know here, like tube-based or bus MPC, to show that you can obtain better performance. In this case, we had a fixed-wing UAV that was flying over the terrain. The terrain is always the same one. Is a vineyard in Lange region. And we were able to reject disturbances, classical things. Then we design for the UGV classical path planner and the local path planner, the combination of the two, in order to find automatically the way from one point to the other. And we design a control law to do this, which is a combination of classical, very simple proportional controller with some quadratic programming to optimize velocity. And we tested these results on the parcel, and they work. I mean, these are still simulation tests, but it seems to work very well. So let's get to how to fuse the information from the sensor, the map, with the UGV. So typically, when you have a UGV going through between rows, you are in a sort of GPS-denied environment. The GPS signal is very low. You can lose it. Of course, you can put an RTK and know perfectly your position, but we I mean, those of us who have experienced RTKs, this is not so simple. I mean, asking the people in agriculture to become an expert in this kind of things, or to put like, to equip all their vineyards with RTK is something that, okay, maybe the vineyard they can say, okay, give me 10, they have a lot of money. But usually this is something that you would not like to ask. So what we were trying to do is to show that maybe using this simple map you can use a simple solution without needing RTK. So the idea is we built a sensor fusion between different filters, and what is the information that you add? The information that you add is the one that you get from, okay, I think this is from these sensors, which are just distance sensors that you put, ultrasound sensors that you put on the vehicle. And based on that information and the information of the map that you have, you can ameliorate your position. And we show that indeed, if you put 1, 2, 3 sensors, you see that the noise is going down. Then we designed a particular, another filter, which is another version of the particle filter, and we showed that this was working very well. But I mean, the main message was just that this idea of building a map and then using the map. This is the main novelty, I think, of this kind of result. One other result, one other goal of this project was to start using UAVs not only for the classical purpose that is devoted to the use of UAVs in agriculture, which is sensing, monitoring. You fly and you have camera, spectral camera, hyperspectral camera, infrared cameras, and you measure and then you decide, or you build maps, you build 3D maps, but to do operations. So this is the next step. So our question was, is it possible to use UAVs in operation? Of course, our answer would be, we would like to be yes. Of course, you have to choose the right operation, and you cannot ask the UAV to go and pick apples, because maybe you can do that, but you will have an UAV that picks one apple a minute if you're very good, and then the guy looking picks 60 apples in the same time. So, but for instance, there are operations like spraying, which are from one side not nice from the point of view of the operator, because they have to, I mean, they are dealing with substances that they would not like to when they use it, they need to wear protections. And then there's, if this is the classical case, in the arable crops, you have even helicopters that do that. So this is technology. When you go to vineyards, you have really 3D crops. I mean, and so the problem becomes much more difficult. So we did some experiment, and we try to understand the feasibility of this. So the first question, and I forgot to. So my question to you was, imagine that you have rows, and you have to fly with a sprayer. So is it better to fly perpendicular to the rows or parallel to the rows? I mean, we had discussions. I was more on this perpendicular solution, because I was saying, okay, while you're moving, you're sort of getting also the sides. Turns out that it is not the case. So we actually, Paolo Gai and this group made experiments, and this solution is much, much better. Why? Because the way they sprayed. So what they did is really do experiments with a sprayer and putting sensors, which are just pieces of paper that when they get wet, they change color, these kind of things, and then you really count the, I mean, it's a hard job, but fortunately, I was not the one to do that. But the solution is that really, you have a decrease of ground deposit and an increase of canopy deposit. So because what you really want is to put as much fertilizer on the crop and not on the soil. And so this poses a really interesting problem from our point of view, which is the one that we are sort of addressing now. These are some experiments. I think this machine is one that will be discussed in the next talk. So let me start it again. The idea is that you want to fly parallel to the canopy, to the row, but usually in vineyards there are rows that maybe they are curving because the terrain is curving, and so you cannot just program. It's hard to program and say that you have to start here and go in a straight line, which is the nice thing that you can do with a new UAV. So what we are looking, this is one of our next projects, is to have an automatic system that detects the row. So you put it at the beginning of the row and you say go, and then it goes all the way up to the. So what the operator has to do is just to put it at the beginning of the row and then let it go. So my work, the work of my group on agriculture, recently moved also to a collaboration with Japan. So I've been working with Japanese people in control for many years for other problems, and lately discussing with some of them, they said, oh, no, now we are putting, in Tokyo Tech, they are putting up a lab on, a friend of mine was putting up a lab on robotics and agriculture, said, okay, we need to work together, we have to work together. I mean, and that's a collaboration that started in 2021, and so what is the idea? The idea is, again, what they had. They have a fleet of drones, small drones, that they use to again, do some reconstruction of a terrain. But then when you get to vineyards, we realize that this kind of reconstruction, where you take picture from top, is not enough, because if you have a vineyard and you have only a picture of top, you don't see the lateral side. So the same point should be taken. You should take picture of the same point from as much possible different direction. So if I photograph this point from here and from here, I have a different information because you have the leaf and everything. So really, they had this coverage control that was working in 3D. Now it has to work in 5D because you have also the angles. So it's a 5-dimensional reconstruction, 5-dimensional coverage. And we did that. We did some experiments. So these are lab experiments, and we showed that you reconstruct much better. Here, I forgot. I mean, I put so many videos that I said maybe it's enough, but you can see, you put a chair and you can see that the chair, you can reconstruct the image of the chair much better, but you can understand. So the idea is that you need to take into consideration also this angle here. So the same point you can see, you want to see it from different directions. And then we went to the field. When you go to the field, you understand that there is another ingredient. So the fact that of the whole fields, you don't want to see everything. I mean, you need to see the canopy, you don't care about the ground. So what we came out is with an automated, or say, we proved that it can be fully automated. We also, regarding the solution about the maps, we proved that you can fully automate that. We don't have the fully automated because after a while it becomes a problem of writing code, and nobody. Okay, now the students are good in writing code, but you don't want them to spend too much time. But we prove that you can do that. So you start with classical tools of image recovery, and you can detect where the terrain is and where you are interested. So you put like a map on top. So the red points are more important, the blue points are less important. It's like you are putting some sort of important function on top of that. And so you can feed this important function to your control algorithm, and your control algorithm will try to I wanted to show you this. Okay, Arti. Okay, so this is a simulation of what's going on, and you see that really they follow the rows and everything. Okay, they have a small experiment going on. These are images that Takeshi just sent me. So I said, okay, I have to have a talk. Do you have? So these are really recent experiments done in Tokyo, and yeah, you see that you can indeed have a very good reconstruction. So I think this. Okay, that was not bad. I mean, I was expecting that half of the video were not okay starting, but some of them are. Okay, no. Okay, but where is that? Ah, okay, see. You can see that you have the reconstruction of okay, this is a fake grape, but you have the 3D reconstruction of the grape. And so that's basically it. I was looking for an image to end my slides, and actually no better image than this. I mean, I'm in love with this image. So, with this, I thank again all of you and all the collaborators that worked on this thing. So, thank you very much.
Thank you very much. I've not seen any question on. Oh, there is one. So probably I just lost it.
Oh, maybe there is a question
but
live.
Let's go live.
Okay, this is a question that...
so the question is which processor algorithm it uses
yes.
for image recovery?
Okay, this is a question that I'm not sure I can reply because it's not myself that I did that. This was work made by my colleague, but they use classical tools. Okay, I have to say that in the years, they have been working a lot on this kind of problems. So in order, for instance, to recognize the vineyards with respect to in a terrain, so they have algorithms based on some transform that I don't recall the name, which basically try to find lines because the main thing is these are lines, so you have to detect lines and then try to fill the gaps and everything. But they have an automatic, I can point you to their publication, they have an automatic way to go from a map to the rows. And then from the rows, then you can do classical canopy reconstruction and this kind of thing.
Okay, so there is a question from Slido that is, do you think it can be justified to use this amount of robots in terms of gains for sustainability?
This is a very, very good question. I don't know, in the sense that my idea of sustainability is that we should move from situations where the tractors are really working in large fields. They are doing intensive cultivations to a field where robots in general are treated like tools. So it's like an evolution of the classical tools of an agriculture, of a grower. So you had very raw tools, and these should be just more sophisticated tools. And the fact that that's why I say they should be green, they should be electric, they should be very simple. I liked what Yael told yesterday. You don't need to have a robot that does 100% of the job. There should be a robot that it's a tool which works better than the classical tools. So that's the idea, and I think that we are just now understanding this. And I think that also in these 4 years of project, this became more and more clear. So we started. You start saying, okay, I want to have a robot that I tell him to do, and then I go, this is not the solution.
Okay. So thank you very much for your talk.
Thank you.
The time, it's something we have to try to keep, even if we are already late, as for our good tradition. So I'd like to invite, to thank you again, and to invite the next speaker. So, yep. So the next speaker is Paolo Marras. So he's the CEO, founder, and I would say also the technical mind behind a small company in northern Italy that is Aermatica 3D near Como. I have met the first time Paolo several years ago. When I had a problem in an European project that I needed drones to do things, and I discovered that he was the right guy to provide me not only with a good drone, but also with a drone that could be customized to my own need. As a matter of fact, I think that customization is your main asset, and the capability to use commercial tool to then generate very specific tools for very specific assets. One thing that I want to say is that the other reason why I invited Paolo is that I know that he has a lot of experience in real fields during the vegetative season. That is something that it's, I think, very valuable, because one of the discussions we had a lot in already yesterday is we develop technologies, why these technologies are adopted or not, and Paolo has a series of success in real adoption of these technologies. So I'm really happy you are here and you can give us your perspective on the matter.
Is it okay? Okay, thank you. Thank you very much, Emanuele. Thanks to the organizing committee for the invitation. I'm really proud to be here today in such a very interesting event. I graduated the last century in robotics engineering at Polytechnic of Milano, so it's the right place where to be here today. Is okay here? Okay, thank you. My name is Paolo Marras. I'm the general manager of Aermatica 3D. Aermatica 3D, as Emanuele was saying, is a small company, Italian company located in the northern part of Italy. We are very specialized in providing application solutions based on drones. So we are able to transform drones in really an applicative tool for several applications. In case it is not needed, we provide a commercial solution. In case requirements do require, we develop a custom solution, and especially in agriculture, we have a lot of experiences. But we work in several fields. Drones can be really a helpful tool for critical inspection in industrial sites. We have just been awarded of a patent, joint patent with Terna, a very big high voltage power line in Italy, for an application of a drone in contact with high voltage power lines. But drones can be automatic flying cameras, visible and thermal, integrated in a total security system. We work with the Italian National Firefighter Department to develop specific solutions for search and rescue. We have integrated very high-level sensors to detect lost people in the mountains, in forests, by detecting their cellular phone signal integrated with drones. We have developed a lot of custom configuration for research centers, as Emanuele was saying, to develop a kind of flying laboratory with high-level sensors integrated on drones. And finally, we have a specific focus on agriculture, where drones are really, really helpful in a lot of application. We are also distributor in Italy of the main provider, main manufacturer of the world, it is DJI Agriculture. So we can provide the commercial of the state-of-the-art drone, but also customized solution. And in particular, in agriculture, why a drone can be really helpful? Because it can do both survey, equipped with visible, thermal, or multispectral camera, but also it can be a small tractor, small flying tractor, able to drop, to distribute product, especially if products are light and can be efficiently distributed on the field. The combination of both tasks, survey and distribution, is in line of the so-called agriculture 4.0. So act only where you need to act. So distribute product, fertilizer, and chemical products only where you need that they must be distributed. And you can discover the area exactly, making survey by drone. Survey by drones can be done by a multispectral equipped drone. And at the moment, a drone equipped by multispectral camera is an operational tool. Farmers, agronomists are using on the field day by day a small DJI drone equipped with the multispectral camera to have maps to discover vegetation index of the field, and then to act according to what they are seeing in that moment. But while multispectral drones are an operational tool, hyperspectral drones and hyperspectral sensors are at the moment research tools. We are providing integrated configuration where a drone is equipped with an hyperspectral sensor, to research centers that are now developing algorithms and softwares to manage very rich data as the hyperspectral are. But in the future, they will help discovering special characteristics in that moment, in that place of the field. So multispectral and hyperspectral data can be collected by drones. But we have also worked and participated in some research projects with important companies and research centers with the aim to discover new sensors that can be integrated on drones to provide very helpful data. In this case, in this project called Pignoletto, as the name of a very good wine in Italy, we integrated hyperspectral radiometric sensors and radiation sensors to provide further data to researchers to identify possible solutions to have more data to discover characteristics of the field. This is not a matter of operational activities day by day today, but these are possible configurations for the future. We have, I've talked about sensing drones, but drones, I was saying, can be distributing tools, flying tools from low altitude of products. DJI Agriculture is one of the most important manufacturers in the world, and if you need to spread liquids or granulates, we have already the right configurations. The right drones, at the moment, you can carry 30 and in a few months 50 liters, and then you can distribute liquids and granulates. Why a drone can be a useful tool to spray the liquids because it's an efficient tool. Really efficient tool if you compare it with the traditional methods. So you can lower distribution volumes and then distribute efficiently on larger area, especially if the scenarios are complex, hills, mountains, and small fields, comparing with traditional methods. So at the moment we are seeing an increasing demand of drones to spread liquids and granulates on the field. Consider last season in Italy we had a lot of floods, a lot of rain, and so in a big portion of the time in the season traditional tractors could not enter in the field to distribute products. We have also to see that in Europe we have a regulation that forbids the possibility to spread the chemicals. Then who is using drones to spread liquid is distributing biological product. And this is another key in the use of drones for agriculture, in the exploitation and in the increase of the biological techniques. I will show you some specific application later more. But when the applicative needs do require a customized solution that is not available off the shelf, we are able to conceive, develop, and bring on the field the right drone solution. So we have a process, development process, and engineering process to design specific solution to bring them on the field and then on the market. We are proud to have already sold some of our units in several countries abroad. Let's start speaking about this solution developed in collaboration with Koppert. Koppert is a multinational company manufacturing insects for biological control. Biological control is really an interesting technique. You don't use chemical products that kill everything in that moment, but use a biological entity to be distributed in the field and then continuously acting during the season. In this case, we have developed an optimized tool to distribute light products. Insects are light products, so the ideal product to be distributed by drone. And in this case, the key is having a commercial enterprise drone equipped with a customized tool, a kit, developed by us to distribute automatically and efficiently on the field insects. The software to make the distribution is really important because in this case, insects must not be distributed all over the field, but they have just to be distributed on the border, on the edge of the field, because they will build a sort of biological wall against the bad insect. In that case, we have developed also the software to plan the automatic flight only on the edge of the field to distribute precisely the insect. And this is an enabling key because insects are valuable. You don't need to distribute kilos per hectare, but just hundreds of grams. So having the capability to precisely distribute insects in the border of the field is really important. This kit has been awarded at EMA Technical Innovation Contest. EMA is one of the most important exhibitions of agriculture in Europe. But we started few years ago with this kit. This kit is the same concept. A small kits, industrialized and automated equipment installed on a drone, able to distribute very precisely material for biological control. In this case, the kit is able to distribute small capsules, very light, that contain thousands eggs of a good insect that once come out is able to parasitize the eggs of the bad insect. This technique is widely used on corn, not only in Italy. We have sold kits in northern part of Europe. We have sold kits in Indonesia. So it's a widely adopted techniques. As you can see, the kit is able to distribute very precisely one capsule every X meter and very fast. That's another key that makes this technique able to be applied on the field. The service provider using a drone is able to cover 100 hectares per day. So it is a very valuable technique. It is a very helpful tool. And biological control is less costly for the environment and the whole chain for the farmer. You can go fast. You can go really in a really effective way, also covering very small fields. The traditional tool is a big tractor that enters the field, wasting some part of the fields, and that cannot be moved easily from a small field to another small field. The drone can be really an interesting tool that makes sense. Obviously, we need to have an automated tool. We have a certified work on the field. In this case, we are able to provide a sort of report with the position, the GPS position of every capsule released on the field, even in case of very complex morphology, as usually is on the field. Capsules of useful insects, but we can also distribute useful insects as living insects. So spread in a small granulates, that is also the feeding medium for the spreading and the feeding medium for the insect. You can distribute Phytosedus permilis on tomato fields, soy fields, and other fields to contrast possible parasites. In this case, we are distributing only on water waste part, Bacillus thuringiensis against mosquito larvae. This is another very interesting application, fighting mosquitoes by using biological product. So we have developed a combined process. Detect the water standing by using a multispectral sensor on top of drone. Then, by using the maps generated by the multispectral sensor used on top of drones, we are able to define areas where to spray in an efficient way Bacillus thuringiensis. Bacillus thuringiensis can be distributed as small granulates. So in a very efficient way, you can use a drone to distribute this kind of biological product. The same distribution kit on top of smaller drone can be used to distribute powder. Mixed in powder, we can distribute pollen previously collected, and then, in case of pollen distributed by wind, the drone can be a precise tool to help distribution of pollen, and then to help the pollinating activity. This kind of technique is used on seeding crops, is used on walnut trees, and it is demonstrated on olive trees. We have attended a long project, 3-4 years project in Italy, in Tuscany, where after 4 years of distribution in different kind of scenarios, pollen by drone, we have been able to have an increase of 20% of production of olives in the field. A really simple task, just to distribute in a precise way powder mixed with pollen exactly when flowers are acceptable. So the drone is just an automatic tool. Some other example of distribution tasks. In this case, we have developed an experimental tool to develop adult insects, used, for example, against vine mealybug, and as an alternative method to go on the field walking and with a small tank, leaving insect flying on the field. The same concept is now being applied to this experimental tool. We are working with a research center in Bologna, in the center part of Italy, that builds sterile male, adult male of mosquitoes to act biological against mosquito in the cities. Now, they are distributed by car or by men in the field, and we are developing a customized distribution tool to integrate on very light drones able to fly in the city centers to distribute in an automatic way and very fast small groups of these sterile mosquitoes spread in the air and able to contrast mosquito problems. Drones can solve also very particular problems. These are the ancient walls of Treviso, in which we worked to make biological weeding with the drone, able to fly in a very complex context and where traditional methods cannot apply. In this case, you can just use a drone to make that kind of job. Once again, not a commercial solution, but a custom solution to make that kind of particular task. Starting from that experience, we worked, it's not starting, as an evolution of that configuration, because different configurations can be used in different scenarios. In this case, drone is equipped with a small tank on board, but a big tank at ground. And with the cable, we are able to use the drone as a flying, moving, acting tool, spraying horizontally to clean vertical walls, to act on very big trees. So once again, from specific requirements, the right solution. In this case, obviously, we have a limit in the scenario because we have the wire to ground, but there are a lot of scenarios where this kind of solution can be really useful and can be effectively used. Finally, this is a set of our products. So we have tried to have a set of useful products for the market and especially for biological control. Finally, just to briefly close this speech, drones can be, for sure, very important remote sensing tools equipped with sensor, but they, complemented with the right kit, can be really an automatic distributing tool from low altitude that can have very interesting effects on agricultural application and on environment applications. Thanks a lot for your attention. These are our contacts. I'm very proud. This is our booth in last EMA fair in Bologna. Thank you.
So, thank you very much, Paolo, for the very interesting talk that I think really complements what Fabrizio was saying, and actually a longer discussion that is going since yesterday about the fact that we have to consider robots of various types as tools that do specific things and that solve specific problems. I have one question from the public that is a curiosity. Did you consider using the drone also for sowing?
It could be. It could be. I can mention a very interesting project where we are working now. We are, for a project, we have won a tender from UN to develop a seeding drone for reforestation in a project in Africa. We are going to modify our capsule distributor to distribute these small seeds for reforestation. So we can develop.
Okay, so it's a work in progress.
Yes.
There is a question from Fabrizio.
Sorry, I was trying to write the question on slide, but so regarding the tethered drone, the drone with the cable, have you considered the possibility of using the cable to feed the drone in terms of power?
Yes.
So you have already the solution?
Yes.
Because this is important, because one of the problems of the drones
Yes.
is that they fly for 10-15 minutes, and if you have a tethered drone...
The question is absolutely centered, because if you already have the link with the ground for the water, it does make sense to have also the link for power. We have already provided some power systems to the firefighters, having power directly from ground, and so the drone can fly hours.
Okay, so since there are, with the time we are again late, but we care up to a certain point because the discussion is interesting, I'd like to thank Paul again for the very nice talk, and to invite our last speaker for this session. That is Jean-François Bastin, who's a professor at the Gembloux Agrobiotech, which is part of the University of Liège. So he will continue on the theme of drones, and in particular his research concerns one question, that is, can we do what we can do with an expensive drone? Can it be done with a cheap one? So I leave you the floor as soon as you are wired. Okay, perfect. So our technical part is ready, so I leave you the stage.
Thank you so much. Can you hear me well? Yes? Okay, all good. So first, I would like to thank the organizer for inviting me to this conference, or to this forum on the use of robotics in agricultural systems. I must start by saying that I think that I'm a tiny bit of an outsider here, because I'm a user of remote sensing, but my background is more about forest ecosystems. So today, I'm going to talk a little bit about the monitoring of ecosystem based on the use of low-cost UAV systems. And I added a little bit small word to my title, which is a towards, because this is actually the direction towards we are going. We are not quite there yet. So a few words of introduction. So I'm an associate professor in remote sensing in Gembloux Agrobiotech with a background in forestry, and I've been asked, invited by my colleagues to try to build a bridge between the research that has been done in Gembloux in the past 10, 20 years using remote sensing, which was more focused on drones, on the other parts of the research that we are doing in the faculty. So, quick word on the faculty. So you know that this is a bioengineering faculty where we work, we develop research on food, on crop systems, on the environment, and on forest systems. So what's one of the big advantages that I see trying to apply my background of remote sensing on crop systems, especially working in Gembloux, is the fact that we dispose of a vast variety of long-term experiments where we can monitor like each leaves of a crop field for maybe, here it's the century essay of winter wheat that started in 1896. So that's, we go way back in the monitoring of crop systems. And in that field, which is really in the middle of the faculty, we follow up like the development of each leaf during the whole growing season for more than 100 years. And we also control various level of fertilizers, including nitrogen, potassium, and phosphorus, on a very, very, very small scale. So that's, for me, it's a big change, because what I'm used to deal with is something which is completely different. So I did my PhD in tropical Africa, in Congo, where we basically have no experiment on the ground. We have almost no data on the ground. We cannot follow up something very closely through time very precisely. And we do not try to characterize like a plot of 1 hectare. We try to characterize the full state of the forest, which if we take the whole tropical forest of the globe, it's about 1 billion hectares. So basically, I've been asked to work trying to build a bridge between those two extreme different systems, and I'm trying to do that in the past 3 years since I arrived in Jean Blou. But I'm not starting from scratch. I'm lucky to have several colleagues which are already quite proactive in that field, not really using remote sensing, but using what I call proxy sensing. And I think that one of my main colleagues working on that field is Professor Benoît Marcatoris, that maybe some of you know. He's focusing his research work on trying to assess automatically based on very fine scale resolution images to describe the state, the health of plant organs, and then combining the different image at the plot level, trying to upscale what he observed at the plot level. So he's really, in his team, they develop robotics, they develop cameras, but really at the very, very, very fine scale. So one of the work that they are doing, which is very promising when you think about remote sensing, it's this. So they try with those robots, they try to collect very fine spatial resolution images at a few meters above the crop with different information also in the visible and in the near infrared. From that, and because they are also taking like a lot of pictures along the way, they are able to take multi-angle pictures from the same elements, so they are able to rebuild a height map by stereophotogrammetry. Then using a deep learning approach, such as a unit deep learning approach, they are able to detect automatically ears of the wheat in the crop, and then we can count them, and we can also build a mask from that in order to isolate them from the leaves. And then using that mask, combining it with the different spectral information that he collected originally, we can try to assess for the different parts of the plant various indicators. So it can be the leaf ratio, the green ratio, vegetation indices, but it can be also the biomass that can be estimated. So for me, regarding the work that has been done here, I thought that, okay, so using spectral information, we can actually do a lot in crop systems. So there is a huge potential of using remote sensing and drones in order to achieve that. So he invited me also when I arrived to co-supervise some of his students. So here I will just present a few more results that are very promising in order to pave the way towards the use of drone sensing in order to characterize health and yields in crops. What you have in front of you is, so they collect, it's the result of a PhD student, which is Yusra El-Mejawi. It was published in 2022. And it was based on data collection from this experiment. They collected leaves from winter wheat according to several fertilizer treatments. So you have the different colors according to phosphorus, potassium, and nitrogen fertilizers. And in the lab, they use hyperspectral cameras in order to reconstruct the full spectral signature of the winter wheat. It was so 1,600 different bands that were able to reconstruct this very precise signature for the winter wheat. The different colors that you can see are the variation of the spectral signature according to the treatment. And using those 1,602 spectral bands into a simple linear modeling approach to try to characterize, for example, information such as the phosphorus content of the leaves, it was working quite well. But this is in lab conditions, so very specific, very controlled. Once you go to the fields, it's a different story in general. But yet, it's a very promising avenue for research in that field. They did the same, not with the leaves, but with soil content. So before and after tillage of the soil, they were trying to assess the content in phosphorus, the available phosphorus and the total phosphorus that you can find in the soil. And once again, using this hyperspectral camera in the lab, they were able to decompose the full spectral signature with a lot of precision, use that in simple linear models, and they were able to develop quite robust model to predict the variation of the available and the total phosphor in the ground before and after tillage. Still in lab conditions, so still very controlled, quite good, but what can be achieved once we try to upscale it a little bit? So they tried to do that as well. So they used a simple multispectral drone, so like it was not a 3M from DJI, but it was, I think, a Phantom 4, sorry, with a simple 4-band camera. And they just tried to maximize the information that you could get from that image. So they reconstruct with stereophotogrammetry a DSM, so a digital surface model. Combined with an available digital elevation model, they were able to extrapolate the variation of height on the ground. They also use spectral information, and in order to distinguish, to standardize a bit the effect of tillage, so the work that is done on the ground, they used spatially informed indicators based on textural indices that can be calculated. The classic one from the Ehrlich indicators, so entropy, heterogeneity, variance, etc. And using those different sets of indicators, they were able, they put everything in a machine learning model, which is a random forest. I said they, but I'm part of that study as well. And they managed to get the result that you have on the right. So it's before, after tillage, and it's the available phosphorus and total phosphorus that is available. What we can see is that at the subplot level, so it's not at the leaf level, so they did a lot of little subplots of a few meters square, the results are quite good. But we need to keep in mind here that it was trained and validated locally on the same site. They didn't have a lot of replicates, while we used a lot of predictors in a very powerful modeling approach in order to get those results. So if you use those models on another field with another image, it's very likely that it's not going to work. But still, it's a very promising preliminary results. Similarly, another work that was done in Jean Blou under the supervision of another professor, not Benoit and not myself, but Jeroen Meersmans, with the PhD thesis of Ramin Decordi. They tried to see how we can use RGB information. So here we are not in hyperspectral, we are not developing complex indicators from spectral signatures, and they were just trying the simplest one that they can have in order to predict the variation of disease on a winter wheat crop field, which is the rust. So the advantage of trying to monitor the rust is that it's very colorful, and you can really see the contrast between the green of the wheat and the orange of the rust. And so this was with a simple modeling approach, just distinguishing automatically the main different colors. So the black for the background, the green for healthy leaves, and the rest for rust leaves. They managed to get quite good results. Once again, it was validated locally. It was dependent on local conditions when they did it. And once you try to extrapolate it on other fields, it doesn't work. Okay, so a small synthesis on the work done in the faculty about proxy sensing. So clearly there is a lot of very valuable information in the spectral signature, but it's not, I think that you all know that. We can go up to detect crop organs and characterize their yields, their content. And also some of the results show that basic RGB information can inform on some very valuable information at the local scale. Problem that I mentioned a couple of times is the fact that this lack of an independent validation. So we are not quite there yet if we want to propose like a solution or a model that can be transposed to other fields, even from the same type of culture. And like the good result that we obtain at the plot scale were dependent on very heavy machine learning approaches, so which present some risk of overfitting in the model. So we still need to do some improvement here. So this was the work done in the faculty focusing on the spectral information, and there is a whole other set of information that can be collected on the field, which is on height. I believe personally that height has more potential in terms of crop monitoring because it's less dependent on like the weather conditions, on sun-seen sensor angles that really influence a lot the spectral signature that you will have in the end. And you have more chance to be able to transpose a model that you develop locally to another system. You cannot do everything with height, but if it is about the monitoring of winter wheat yields and biomass, this is basically very related to the height of the crop, so it can already be something very interesting. And in the forest system, it's something that we study a lot in order to characterize the biomass and the carbon content of the forest, so it's a bit more related to the recent study that I've been doing. So the work that was done in the faculty, they first tried to see if they were able to recover precise height measurement with a basic reconstruction of stereophotogrammetry with a drone. Again, it was, I think, a Phantom 4. And they compare it with a very precise measurement of the height using a terrestrial LiDAR system, which was the FARO. So the FARO is scanning in 3 dimensions, very locally, the whole system, but a very, very, very high level of precision. And actually, they managed to find a decent relationship between the two. There's a little trick behind it, but I will comment that a bit later. And so developing the relationship between the UAV-based assessment of height, they use that information afterwards in order to predict variation of winter wheat yield and biomass. And this is the result that you can have, that you can see here on the right, on the bottom. Actually, I think the graph on the left here is only using the spectral information. So they combine several vegetation indices, and the one that is less biased, it's not really obvious, but it's less biased on the right, is also combining spectral information with height estimations from UAV. So from that, they were able to assess the evolution not only of crops, which are quite controlled and where we can really follow up evolution through time of growth, but also of pasture, which is a bit more complex to follow up because it's much more heterogeneous, and also the variation of height that you have in pasture is not from 0 to a meter if you follow up the whole growth season of winter wheat. It's just a few centimeters, and it's changing a lot depending on the animal activity on the field. But they had decent results in order to understand, then they can use that afterwards in order to understand the behavior of sheep and goats and cows which are active on the field. But the thing is that if you dig a little bit on those studies, so it's nice, you have the impression that you can use a basic drone in order to characterize variation of height of pasture, which is very complex system to characterize. But the thing is that you realize, if you go in the supplementary of the methodology, that in order to do that, they needed 2 key elements. One of the key elements that they needed was they needed a differential GPS in order to make sure that the level of precision of the geolocation of the image were like below 1 centimeter. So it needed to be very, very, very precise in the 3 dimensions, X, Y, and Z. And they also needed to have a digital elevation model, so a map giving you the altitude, basically, with a very, very fine resolution as well, 1 centimeter. Which was synchronous with their assessment of the field with the photogrammetric drone. So that's a lot of condition. And In those times, it was published in 2019, but it was about a crop that was monitored in 2015, and we were lucky in Belgium because we had the first LiDAR flight by plane that was done all over the region, and so we were able a bit to, at that time, to collect information that we could relate to the digital elevation model in order to follow up growth on a pasture or on a field. But you need to realize that for pasture, so for a grassland, for example, it's a few centimeter difference that we are assessing. So each time you work a little bit on the field, each time you have a season of animals that went into your field, this changed like the variation of heights of the ground for a few centimeters, so it messes around with the result that you can have. So it's very important to have a good synchronicity between the DEM and the DSM here. So this is a bit basically what I just told you. So it's good, but it relies on a lot of conditions. And now what I'm going to present to you very quickly is the challenge that I pose to my students. So I'm teaching partly smart farming for master's students in agronomy in Jean Blou. So I have only 5 classes with them of 2 hours, and my aim is to try to see if with those 5 classes they can reach a level where they could monitor their crop or a given field with a basic drone. Building on the knowledge that was built in the faculty before. So one of the recent ideas that we had is that we could try to solve the latest issue that I mentioned about geolocation and the dependency to the digital elevation model by reconstructing a digital elevation model directly from the drone flight. It will not be necessarily like good at, it will not fit with national maps of digital elevation model, but in the end we don't really care, because what we want to do is we want to have an estimation of the height of the ground and the height of the top of the canopy locally. Whether it is correct that we are at 100 meters or 150 meters of altitude, we don't really care. We just want the difference between the two. And basically the best way to do that is to use the same flight with the same product, so that you have the very good georeference, geolocation between the two. And so you basically get rid of that issue of geolocation. And also, if the spatial resolution is good enough, you can build a DEM which is at a good quality, depending on the crops, depending on the system that you're monitoring, of course. So using a structure for motion reconstruction of the digital elevation model and the DSM, we follow those different steps for the century-old essay in Jean Blou. So this is the DEM, this is the DSM, and then doing one minus the other one, you can build a map of the height of winter wheat for that period. So this was a flight that was done in June 2023, so last June. And to get some result that looks interesting, so you can see here it's a variation of altitude from between 0 and 1 meter, so it seems correct at that level. The students in their 5 classes, they didn't have much time to develop a complex approach in order to model the variation of height or biomass in that field, so they just did linear regression. But I like those kind of approach because it's very simple, and if you don't see anything with linear regression, that means for me that it's going to be very complicated to see something here. So you have a first very preliminary result, which is the relationship between the two, so the predicted height and the biomass that was very precisely measured on the ground. You can see that there is a relationship, but there are 2 or 3 problems. The first problem is that you can see that you have 2 assemblage of points which are probably related to 2 different treatments in terms of fertilizers. So we still need to work a bit on that to make sure we are able to standardize the relationship. And also a big problem is that, well, what you detect with that kind of approach, you detect where you have almost nothing and where you have a lot of wheat, basically. So it's a bit of binary information that you get. You don't get like the whole in between that you have with intermediate level of treatment in terms of fertilizers. But one thing that we could do for that is just to combine it with a classic spectral information, which is collected at the same time. It's the same same drone flight, same pictures, so that's convenient. And you have here the NDVI, the famous NDVI that is presented on the right, and you can see that there is a correlation between the two, which was expected. And also we, in places where the height extrapolation that we made didn't detect much, we detect a little bit of information here with the NDVI. So probably here the idea will be to combine the two in order to develop a simple model, simple linear model that will provide good results to monitor the variation of height in a winter wheat field crop. Sorry. Last but not least, I challenged also another group of students to try to do something that is for me quite impossible to do. So I gave them the worst drone ever that they could use, which is the DJI Mini 2. If I'm saying the worst, I like it very much. But in terms of monitoring, this is not probably the drone that you guys would use. And I tried to ask them to monitor the state and the variation of height of the worst probably system that you can find, which is a green meadow, where you can see that what you have variation of height, but it's very low. It's maybe between 0, 5, and 10 centimeters, and it's not very homogeneous. It's not like you have 10 and then you have 5 and then you have 0. It's you have little bumps of everything everywhere. So I was just willing to see if they could get something out of it. And the results are not exceptional, right? As you can guess. But we detected some kind of trend. So, meaning that I think that we had, basically for that, we had to develop a customized field inventory in order to make sure that we could not use the classic SWAT stick height, like leaf by leaf, in order to estimate the height on the ground. We had to do like little plots, but even with that, it was impossible more or less to find like homogeneous areas to train the model. So there is a lot of issue in there, but we find a trend that is not completely stupid, still using a simple model. So I think that with those results, this opens the door to the development of very interesting monitoring with drones, using low-cost drones for food systems. Thank you for listening to me. No, sorry, I forgot. I forgot one thing. So the perspectives. So where do we go from there? Sorry. What we will do this year is that we will take advantage, as I told you, of this long-term experiment that we have in the faculty, and we will do. Now I have the chance. After a couple of years, I managed to buy a couple of drones. So we have a LiDAR, we have thermal drones, we have the 3M multispectral, classic multispectral, and we still have our Mini 2, and we will do every 2 weeks a flight with all the drones together to monitor the state of the system. And we hope that combining LiDAR with a drone with multispectral thermal, we will be able to characterize it very closely and see what we can get with the Mini 2 here. Because my goal basically is to be able to convince farmers that using a drone, a simple drone without a lot of technical skill, can already give you a lot of information on your field and to help you into the monitoring and the management of your farm. Now that's it. Thank you for listening to me.
Thank you. Do we have one fast question from the public? Well, if not, I have one that it's something we were already discussing a little bit of offline. That is, in our experience, playing a little bit with this camera, but much less than what you have done, we have seen that it seems that everything depends very, very much from the crop, the specific situation, and so on. What is your approach as a curiosity? You try to select crops where you have good hope, or you try the other way around?
But as you have seen, I think that we work in both cases, in the sense that we work on the wheat-to-wheat, which is very well controlled, and we can really like have on maybe 1 or 2 meters square, we can have huge differences in terms of density and height. So that's one way to go. But I really would like to be able also to follow up what's happening in pasture, because I have a colleague of mine, Jerome Bardel, he's very interested into forage behavior. So I would like to go into those very complex situations. But what I believe is that, I told it I think in the presentation, it's very complicated to develop an approach which is based on spectral, hyperspectral information that will be, that you can generalize outside of your lab or like field of study. I think that one way really to go is to focus on height. Height will be like more general, and regardless of the species or the type of crop that you are going to use, it should be transposed to different systems. So I have good hopes that focusing on height, and this is why we bought this LiDAR drone, we will be able to develop something a bit more robust.
Thank you very much. I also wish to say one thing that is for the non-Belgians in the room and at home. The Gembloux Agrobiotech is a very well-known center here in Belgium. Actually, until a few years ago, it was an independent university focusing on agrobiotech. Now it's part of the University of Liège, but it's really a point of reference here in Belgium for everything that is research in this field. We are very grateful for their collaboration in this event, for the talk that we have just heard. And among us, we have the Dean of the faculty that is a co-organizer of this event. It is with us. It is Frederic Francis, and will be the chair for the next session. This said, thank you again for your nice presentation. And I think we can all go for our well-deserved coffee.
Okay, so I propose to you to start the next session. So I feel that normally after the coffee, it's really more than wake up or a second wake up. So it's really my pleasure to welcome our colleague Mario Contarini and Stefano Speranza. I don't know if both of you are speaking or not, but I'm presenting both of you. So I let you the share, and we are really very curious to hear about pest management, and I would say I let you the floor.
Thank you very much. My name is Mario Contarini, and I'm an insect scientist, and I work at the University of Tuscia in Viterbo, and today I'm going to talk about insects and the sustainable pest management. First of all, let me say thank you to Emanuele, to the BrIAS, first of all, Emanuele, Luca, and Anja, and everybody that hosted here in a very kindly way. Okay, so let me introduce the topic of my research, insects. Insects is a very interesting group, since it has a long history of evolution, which is started more or less 400 million years ago. And in this huge period of time, this group has differentiated in more than 1 million of species with very amazing features. Now this group, as I told you, which is represented by more than 1 million species, represent a large part of world biodiversity. Just to give you a comparison, birds are about 10,000. So it's a very big difference between insect and all the other group of animals. Okay, in this very long evolution period, a huge variability of forms, colors, behavior can be now observed. And, but the most important thing is insects are, play very different roles in natural and agricultural ecosystems, and only a small part of them is detrimental for the production. On the contrary, we have to say that the large number of insects are useful for our ecosystem. Just to think about pollinators. Insects can be identified very quickly, more or less, for the presence of 3 pairs of legs, up to 2 pairs of wings and 1 pair of antennae. Among the many features that insects have, one of the most important is the ability to fly, which is a very important mean to spread, searching for food, for a partner for the reproduction, and also for just to escape from a predator, for instance. Insects generally have small size, and we can say that the majority of insects have a dimension that is less than 1 centimeter. Although we can find also insects that are very large and also big in length. This small size means that these organisms can constitute large population in small habitats. Another important thing is that insects have a sexual reproduction, but also a parthenogenetic reproduction. It means that in the reproduction, males are not involved. And this is important in those organisms that colonize new areas, since this fact that one specimen is sufficient in the colonization phase, and this increase the chance of success in the colonization phase. The life cycle of insects is divided into stages, with young and adult that often are morphologically different, and also that sometimes live in different ecological niches. Another feature is the presence of exoskeleton, which is a stratified structure that offers protection to the insect, and that is characterized by high mechanical resistance, efficiency, and light weight, and it is also effective in the water balance, in the optimizing of the water balance of the insect. In this image seems to look at a leaf. It seems a leaf. Instead, this is a Lepidoptera species. So insects have this huge capability and huge attitude in the mimicry and camouflage. And this is important because reduce the chance to be detected by a predator or parasite, by a man that wants to monitor the species, and also reduce the opportunity and the possibility for the detection, the automated detection systems. Another feature is the adaptability. It means that we can find insects from the poles to the equator, living in habitats with extreme climatic condition, temperature, humidity, and so on, feeding on a huge source of food. And in particular, most of the insects that we have in the world are feeds on plants' parts. It means seeds, leaves, fruits, and so on. The relationship between human and insects has a whole story. Humans have always fed on insect or on their products, and humans also they started to imitate them. So we can talk about bio-inspiration, as we can see in these images, where the giant Magellan telescope reproduces the eye, the compound eye of the insect. But now if we can talk about biocompetition, since insects are the major competitors with humans for resource produced in agriculture. We have to think that almost 20% of annual world agricultural production is affected or is destroyed by the action of insects or mites, with an estimated value of more or less $500 billion. And with also indirect economic losses that are caused by the management of these insects, of this pest, and environmental contamination. In the past, the management resorted to calendar-based pest control or identify and spray pest control, which had, of course, a very negative impact on the environments. Then it has been introduced another concept, the economic injury level, that Stern defined as the amount of pest injury which will justify the cost of control. And with this introduction of this concept, we went in the integrated pest management, which is an approach to solve pest problem in an economically viable, a socially acceptable, and environmentally safe manner. This approach can allow a more rational use of pesticide, an improvement in agricultural product quality, and in a reduction of negative effects on non-target organisms. In Europe, the insect pest management is a process that must consider biological, environmental, toxicological, economical factors. But there is another thing, is regulated by European and national laws that require that farmers make a choice between two different phytosanitary strategy or management. The IPM production, in which chemical pesticides are regulated in terms of number of treatments or in terms of phytosanitary products that can be used, but in the IPM, the use of chemical pesticide is allowed. On the contrary, in organic production, synthetic chemical pesticides are not allowed. One of the aims of the European Green Deal is a reduction of, is a 50% of reduction of the most harmful pesticide by 2030. But with the protests of farmers, let's see if we'll see some delay or something like that in this objective. In the pest management, we can divide the pest management in in different steps. The first one is the field monitoring. So an operator, that can be the farmer or an agronomist, must go in the field, look at the field, look at the crop, and the other step is the pest identification, which is a very important step. Then, if integrating all of this information and integrating this information with the climatic condition, with the practices, the agronomic practices in that field, all of this information must be analyzed. And if the target organisms is above the threshold, control action must be performed according to the phytosanitary management that the farmer has decided to adopt, organic or IPM. Okay. Monitoring is a quantitative assessment of insect population density in a defined area and over time. It means that it has to be repeated along the season, which is an important effort for the farmer or for the agronomist and so on. Let's try to make an example. If we have a 1 hectare vineyard where there are 2,000 plants and each plant has 4-5 bunches of grape, if 30 seconds is the time for the visual monitoring of each bunch for the presence of Lobesia botrana, the time that we have to invest in the monitoring activity, in this monitoring activity, is about 80 hours per week, which is an amount of hours, a very huge amount of hours. So monitoring must be on a sample basis. It means that we have to choose plants that represent the crop. And, but also the sample basis increase the uncertainties. And another problem for our entomologists or pest or insect scientists is how accurate is the correlation between the monitored population and the population of insects that is really present in that field. This is a very huge question mark. Thank you, Luca. So monitoring is a high-cost activity and requires another important thing, requires years of experience of the operator. Okay. Generally requires that a person goes into the field periodically, and this person needs to have uncommon skills regarding the knowledge of strategy for the collection of that pest, the identification of that pest, the biology, and so on. The traditional insect population monitoring can be conducted using visual sampling, as for instance that we can use for the monitoring of Lobesia botrana, as we talked a little bit ago, or plant parts collection sampling, or using some instruments like traps that are chromotropic, if are lured with the color or with some chemical like food or pheromone. But a problem that we are facing is that what if visual monitoring has to be done at 20 meters height into the tree canopy? This is the problem that we are facing in the case of this insect, that is called Tumeiella parvicornis, that is endangering the iconic stone pines in Rome, creating a very huge problem. So robotics, can robotics give an help in the resolving this issue? Identification of organisms and data analysis are processes that require expertise, instrumentation, and time. First of all, we need a microscope, stereoscope for the observation of morphological characters, and these are important in the use of specific dichotomous keys that are important for the identification, the specific identification. And all of this information, monitoring, identification of the pest, the environmental factors, the agronomic management can allow a detailed analysis of the situation. All the data collected are useful in the development of DSS, Decision Support System, which are computer-based tools that can assist farmers in the decision-making processes by implementing multidisciplinarity. This system employ automated traps, for instance, and all of this information are integrated with highly detailed climatic data in order to allows the application of mathematical models that can be useful in the description and the prediction of population, insect population outbreaks in the field. If the presence of the pest is high, has overcome the threshold, control action must be taken, must be applied at the right time. And if we are in IPM and organic management, you can use agronomic practices, biological or microbiological control, physical or mechanical control, and so on. Only in IPM production we can use synthetic chemical pesticide, which should be the last option in the control of an insect pest. A little bit of history of smart traps. Smart traps have more or less 40 years of history. This that has been developed by Hendrix, seems to be probably the first smart trap applied in entomology. And here in the mid-90s, we observed this trap where was the first application of camera for the monitoring of an insect. Now, smart traps in the agriculture 4.0 integrate an hardware and a software. The hardware is constituted by the structure of the trap. The lure, it means the means for attract the insect. A camera or a counting system, a modem, a battery, and or a solar panel. The software represented by the online archive and algorithm for automatic insect detection and counting. And here we can see some of the most common used automated traps in many parts of the world. And in the monitoring of this insect, which is the Aleomorpha alis, we tested, maybe I have to make a step back. What we want to say is that a multidisciplinary approach is essential in the development of smart traps. This is what we saw last year when we tested this trap. Oh, sorry. This kind of trap, and that has a counting system here that is activated when Aleomorpha alis goes in. The fact is that this insect likes the narrow part, so it likes to stay here for a long time sometimes, and goes in, go back, go forward, go back. So activating many times, many times the counting system, even though the insect is just one. So this is what we saw is a problem in the counting of insects. Concerning the detection systems of pests, the technological advances now are lead the development of 4 different strategies. The computer vision that uses machine learning algorithms such as the convolutional neural network, or the acoustic monitoring, which is a very promising aspect, the radar, and the molecular methods which use the genetic information of insects. Let me now talk about our experience in the Pantheon project that has been conducted with we heard yesterday, Andrea Gaspari and Martina Lippi, Valerio Cristofori, Emanuele, also from ULB. We worked on hazelnut gall mite, which is a very tiny mite that colonize buds, and during the colonization of the buds turn into galls. It means that they lose their viability. Of course, the assessment of this infestation is time-consuming, since a guy must go in the field, check for infested buds and healthy buds, and count the one and the other one. We resorted to YOLO system for the detection of galls and the discrimination from galls to healthy buds, and we obtained very interesting and very promising results, about the 86% of correct in this discrimination. And in addition, we identified the section part where galls are more concentrated, which is between 150 centimeter and 300 centimeter from the ground. So this part should be better analyzed in the monitoring activity, because there probably, not probably, for sure, there is more concentration of these galls, and this is very important because give an important help in the monitoring and in control phase. Now we are working in another project, which is called the Masternut project, that has been funded by the Ministry of University and Research. And our aim is to evaluate new automated mite collection system, such as the cyclonic spore trap or the pollen sense. And we want also to experiment and test the automated detection with molecular method for the cyclonic spore trap, and the YOLO system for the pollen sense. In conclusion, we can say that insects are very complex organisms, and these organisms are fundamental part of complex system and in ecosystems. Monitoring is a time-consuming activity and subject to uncertainty, and even if promising results have been reached in the last years, there is still much to do in making the collection and detection of pests more effective. only a multidisciplinary approach with the application of innovative methodologies can help making the management of these organisms more sustainable. And thank you very much for your attention.
Thank you for this very good introduction and making the link between entomology and, I would say, robotics and so on. So I don't know if you have any question. Yes?
Thank you for the presentation. You had sustainability in your title, and you said, I think in the beginning, that about 18 to 20% of the crops are lost due to insects. So we can consider there's a lot of insects, or a huge amount of insects that feed on the crops, so to say.
Yeah, they cause a reduction of production in several ways.
Yeah, and with sustainability, and given that biodiversity is also a part of sustainability, has there been any research on if you would reach, I don't know, 5 or 10% or 0% of losing your crops to insects, how many insects would die or vanish from biodiversity, and how that affects maybe sustainability in that way?
So you are asking if we can find if there is a way to defend the sustainability using other insects. I don't understand, sorry.
No, sorry. By reducing the amount of crops that are lost to insects, you would probably also reduce the amount of insects, right? We would kill or like reduce the amount of insects that are on the field or generally.
This is a problem. Yeah, the use of pesticide has a very huge impact on the insects, and the problem is that the impact is on the pests, but also on the useful insects, even though useful is a bad word for me, because all the insects are important for the ecosystem. So probably the most important thing is to try to reduce the input, the chemical input in our field. This is probably the only thing that also the European Green Deal wanted to achieve.
Okay, thanks.
Another question?
I saw the case of the insect that moves back and forward, back and forward, back and forward, and increase. So misstate the measurements. Do you think to have some mechanism to avoid maybe suction, to avoid the insect can?
This could be a very good option. Yeah, because they like to stay in that narrow part. So
but
if there is something that
which kind of sensor do you use? The counter is made with a laser.
Yeah.
It's the tradition.
And if
maybe the eating of the laser is something that attracts them. Maybe, I don't know, but you have to make some mechanism to force them to go away.
Yeah, this is the idea, but could be very interesting. Yeah.
Yep, we can work
because
together.
They like to stay there.
Like a cat on the car, because it feels heat and it saves energy at the end of the game. So maybe.
Okay, only to explain that the knowledge about the behavior, the ethology of the insects is really important, because it's more or less easy to build traps. But if you don't know a lot of insect science, of entomology, and the behavior of the insect, you collapse your activity, and then you don't have the useful action in this. For this, multidisciplinary approach is the base for us. Thank you.
Okay, so thank you again, Mario. So I propose to switch to the next speaker, and it's my pleasure. Sorry. And it's my pleasure to welcome Francesco Lamonaca. And he will speak about the measurement community and the support for the, I would say, smart or precision agriculture.
It's okay? Yes, sure. Here we are. It's fixing. Okay. So, first of all, let me thank all of you and Emanuele, Anja, BrIAS, because I'm learning a lot. I'm a metrologist, I'm a measurement guy, I'm dealing with measurements, and it's very exciting for me to stay here and to listen to your speech. So I have a little bit modified, as usual, the presentation up to the end. And Emanuele asked me to talk about what measurement community should do to support precision agriculture. And this is a very interesting but also very difficult topic for me, because we have to move, the interdisciplinarity is something that is very common for my community, because measurement, everybody do measurements. So, but create a formalism to give us the scientific approach of metrology science means to talk with the expert in the field, because often the main problem is the definition of what we have to measure. And this agriculture is a typical case, especially when we move from the laboratory into the field, into the orchard and so on. So this is the agenda of this presentation: agriculture between past and future, the role of measurement science, and with the artificial intelligence, with the robotics, we have heard a lot about this. Some open challenges and the conclusions. Why talk about agriculture between past and future? Because agriculture is not only a techniques, it comes from a need, but after it becomes a revolution. It becomes a revolution in the culture, it's become a revolution in the way in which humans start to think themselves into the world, how to see the world, how to measure the world, how to interact with the world. In particular, the first revolution in agriculture was about 12,500 years ago in the Neolithic. It was a transient, it was a passage between hunters to peasant, between nomads to settler, in the social way, the matriarchy to patriarchy, and from fight against the nature to use the nature, from be guest of the earth to be owner of the earth, from stars to moon as a unit of measurement of the time. What we have with this transition, different kind of food, a surplus of food. We start with the deforestation, we had the demographic changes, and we have also economical exchanges. So, which is the role of the measurements? Of course, we need to quantify goods in order to have the barter. We need to quantify how many seeds I have to save for the next year. We need to measure the land, because now I am owner of the land. And consider that we have also a demographic transition. People start to live nearby to the rivers, thinking for Egyptian, for example. And the Egyptian need to measure the land, because each time Nilos go out,
they lost the references. So how I can say where is my piece of land? And consider that Egyptians developed what we have developed 1,000 years later. I mean the meteorological chain. Of course, they use the arm of the pharaoh as unit of measurements, but after they fix this in stone, and then all the guys that measure the land, geometer, have to tune each new moon a piece of a stick of wood with this stone. And of course, if they do not do it, there are subtle check. If they do not fix with the right compliance, they will be killed. So we have something like 1% of error up to 200 meters. So a very easy technique that we have to wait 1,000 years later to have again this meteorological chain. In the second revolution started in Great Britain, as we see yesterday, very interesting presentation from the historical point of view, and in the 18th century, where we applied the techniques, the machines, we start to apply the machines to the agricultures. And of course, it gives us a huge quantity of food, but also we had a change into the demographic population. They move from the land into the city, because now we have no need of a lot of people that have to work into the land. And we have also, we start with wasting food, and we have a revolution as concerning also measurements, because in this part, measurements from mechanical and thermal measurements play a key role. And as you can see now, the role of measurements, but also the effect of the revolution in our life as humans is huge, it's very, very evident. In the third revolution, it started with the beginning of 1940s, with the Second World War. There was hunger, so against the need to have more food. And in this moment, we start to use chemicals. We start to select, so we have a genetic selection of the plants. We had a lot of food, but at the same time, we create a fertilizer dependency. We create seed sterility. And, but we encourage, strangely, we encourage pest and plant resistance. And we create also health problems for people. Why? Because when they measure, this is the moment in which we have some pesticides like also DDT, for example. The guys that invented the DDT took the Nobel Prize because they thought that they have invented something that works on mosquitoes but not on humans. But because we do bad measurements, we make short-term measurements instead to have long-term measurements. In this case, the key role was from chemical and biological measurements. Now we are in the fourth revolution, or the silent revolution, that is the precision agriculture, that deals, as we have saw, with efficiency, sustainability, optimize the resource utilization, and it comes from data-driven decision-making, efficient applications of resources, tailoring resources based on real-time data, and the use of artificial intelligence for forecast and decision, and robots for online decision based on measurements that we took directly in the field. But of course, behind of all this, there is much more: measurements. Why? Because this revolution comes with information, and objective information means measurements. So, in a very first approach, which is the role of the measurements? Of course, the evaluation of land health. I can measure the structure of the land. I can measure how much water there is into the land, the pH, the nitrites, and so on and so on and so on. But we can measure also the quality of the seeds, how the plants are growing, their health, the quality of the crops, which is the effectiveness of pesticides, and when I have to use pesticides. Indeed, with my colleagues and friends, we have talked a little bit, And they explained to me that pesticides show us the biocompetitors deals when the insects are in a particular stage of their life. So it means that if you apply these pesticides or bioenemy when they are in the wrong stage, there has no effect. And the problem in this case is that the life cycle of an insect is a problem because it is not depends from the moon, it's not depends from the time, it's not like 9 months like humans or mammals. It depends on the weather conditions, it depends on the availability of the food, it depends on the hormones, it depends on other chemical stuffs that the plants generate. So the model is a very big trouble. By using a measurement terminology, is the definition of the measurements, the uncertainty on the model. So this is a very complicated task. But also, measurements help to understand the harvest time, so we avoid the waste of food. And these harvest times is also something that is very variable, especially now that we are living changes in the weather conditions. And, but measurements do make more, because now we need to store the food, and the environment where we store the food is as a paramount important to avoid waste, to maintain the organoleptic properties of the food. So we need to guarantee through measurements the right conservation path from the harvesting up to the plate of people. So we are starting to talk about biopackaging with sensors inside the packaging. And this means that we have to measure that this biopackaging, these new sensors, do not affect the health of people. Now it's, we heard about comestible batteries, so I mean batteries that we can eat. So this is a new paradigm. Of course, on the basis of this evaluation, there is the sensing. So metrologists help not to build the sensors. This is a task that comes from electronics, from chemicals guys, from who study biology and so on. But to choose which sensor is more suitable for these particular applications. But before to select the sensor, we have to understand what we want to measure. And this is a problem, especially in agriculture. Then the communication, the paradigm of the sensor. The paradigm is changed. Now we go through sensors that are spread into the yield, sensors that can be sacrificable. I mean, I can left them, they die, and it's okay. But also we have another centralized approach, for example, by using hyperspectral images into the visibles that come from satellite, but the satellite has the problems that are not always available, maybe sometimes are not freely accessible, and the resolution maybe cannot be sufficient for my particular application. So thanks to the research in sensor, we make sensors smaller, we make sensor cheaper, we can mount them on robots, we can mount them on drones, and we can achieve higher resolution. And now there is a huge opportunity, of course, but also a problem. We have a lot of data, and we need to extract useful information from data. So what is the panacea of all problems in this, another open problem is the evaluation of biological phenomena. So it's the things that I've talked before, for example, for insect. So the panacea is to be artificial intelligence. With artificial intelligence and machine learning, we can detect predictive models for crop yields, recognize patterns, optimize the use of resources, provide decision support to the farmers. And another nice aspect of artificial intelligence approach is that it adapts itself on the basis of new data. It means of new measurements. When we merge robotics with artificial intelligence, we have robots that are able to establish by themselves, for example, the rate where to plant seeds, where to plant crops, and so on the basis of direct measurements that they done on the land. So as they decide what fruit must to be harvested or not, make yield monitoring to give data to optimize the next generation of harvesting, and monitoring and surveillance, direct monitoring and surveillance of the land and to the field by driving in autonomous way. We have so many presentations about this, so I don't want to spend many words on this, but it's fundamental to understand that all this can be done thanks to measurements. So robots can work, can interact with each other by exchanging information that are measurements. Artificial intelligence, the effectiveness of the artificial intelligence depend on the quality of the measurements that we give as input. And also another problem is how to present these new technologies to farmers, to the stakeholders. We need to present them by using data, objective data, I mean measurements. And also we need to assess interoperability. Interoperability between heterogeneous device and sensors. And interoperability deals with measurements, because in order to assess interoperability, it means that we have to define standards. And we have to measure in order to check time by time that these standards are respected. But make a step behind. What are measurements? Measurement science aims to retrieve objective information about properties of physical phenomena and magnitude. It means I cannot measure an apple. I can measure the weight of the apple, the color of the apple, the organoleptic properties of the apple, and so on, but not an apple. And the problem is that this information is not absolutely true. I mean, it is affected by uncertainty. What does mean uncertainty? We have potential error, so we have some error that we can know, but there are potential error that we doesn't know, and we have magnitude of influence that affect my measurement procedure that create uncertainty. So measurement is not an exact science. And this is an experience of everybody that works with real experiments, that when we are measuring the same measurement many times, we cannot achieve different numbers. So we have to deal with statistical tools, especially with statistical inference. Why? Because in theory we can make infinite measurements, but it means to use infinite resources. So measurement have a cost. And so I'm trying to infer information about the measurement value on the basis of a small set of measurements. The measurement itself can change during the measurement process. The measurement can be, we can do direct measurements, but often we achieve information by indirect measurements. I mean, I need to have a model of the measurand, and I infer information on the measurand on the basis of the information that comes into this model. Of course, a model is something that is not the reality, it's a simplification of the reality, and this simplification means introduce an uncertainty. But also the unit of measurement that I am using in that moment is not the unit of measurement, the kilograms that is saved in France. Is a reproduction, and a reproduction means that it's different, and I know which is the difference then to the metrological chain with some uncertainty. And this uncertainty comes into the uncertainty that which whom I will know the measurand, but also the experience of the operator, the measurement method that I'm using, so as the measurement instruments. So it is urgent to quantify the quality of the measurements, I mean the uncertainty. So, as Socrates says, "Scio menil scire," it is Latin, I mean I know that I don't know, but strange if we know the uncertainty, it is the basis of our knowledge to take a decision. There are several ways to evaluate the uncertainty according to the measurement method, this particular case, and we have the Bureau, the International Bureau of POI measurement, give us a guide that for us, from methodology guys, is a Bible, that is the guide to the expression of uncertainty, that as you can see is 2020, the date of the release, and we have another one. So as you can see, measurement is not something that was developed some years ago and that's it. Consider that in May 2019, we have changed the definition of unit of measurements. That for you, nothing changed. For us, it is a Copernican revolution, because we have defined the unit of measurements on the basis of the fundamental constant. It means, since the fundamental constant are with no uncertainty because they are agreed politically, we know that these are the values, and that's it. It means that in theory, we have defined the unit of measurement without uncertainty. In practice, we have the uncertainty because we need to realize them, and so the uncertainty in this case depends only on our technical capabilities, but not comes from the definition. But for you, nothing changes. And the definition in GUM of uncertainty is a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. The word reasonably in this slide is a key that let us understand that uncertainty cannot be calculated. Uncertainty can only be evaluated, and this evaluation depends on the capability of the operators, but also from its moral integrity. Because in the next example, I can show you as if we make a trick on the uncertainty, we can say everything and its contrary. So, why it is important to evaluate uncertainty, understand the meaning of a measurement, compare measurements, make informed choice. This is a typical case. I'm acting in a greenhouse. I would like to increase the temperature, so I'm doing something. The temperature, after an interval of time, the temperature passes from 38.2 to 38.4. Is the temperature increase significantly? We can say nothing. We can say nothing if we do not quantify the uncertainty. Indeed, if with my measurement process, the sensors that I have an uncertainty of 0.5 degrees, and let me know that this is a good result for temperature, these numbers mean practically the same things. We have to do nothing. If I change my measurement procedure, I'm changing the sensors, I'm changing the method and so on, and I can achieve an uncertainty of 0.01 Celsius degree, it means more expensive measurements, so I can say, okay, there was a significant change of temperature. So, too great uncertainty makes the results unusable. But as we saw in the past presentation, the trend is to use low cost, low cost, low cost, low cost. But low cost means big uncertainty. So how we can deal between the need of low cost sensor and the need of meaningful measurements? I mean acceptable uncertainty. Also because when you start talking with people and you start talking about uncertainty, they start to be scared. And when you say, which is your desired accuracy, they start to give you some 0.000001 because they do not accept the uncertainty. But when you say, okay, you have to pay this, no. They refers to Chinese devices. No, Chinese devices are also good, but they want the ones that cost 20 euros. So, From this, I have just added a small informative bit to your knowledge. I mean, I am trying to help you to consider this aspect because I'm pretty sure that you already have this. So which are the open questions for measurements? First of all, what is the measurand? The definition of the measurand. And in smart agriculture, this is a problem. Sometimes this is a problem. What is the desired measurement accuracy? These are questions that we are typical says to the expert into the field. Which sensor must be used? How to extract the measurement information from the sensor data? Because what we receive from sensors are not measurements, are just data, are just signals that we need to elaborate in order to have measurements. Then, where, how often take measurements? And this is another huge problem in agriculture, because increasing the place where I'm taking measurements, increasing the frequency with whom I'm taking measurements means not only increase the cost, but also increasing the difficulties with whom I have to manage data. And this is another problem. So, how to assess the referability of the measurements? Often people use instruments that do not take care about the calibration certificate. What was the last time that it was calibrated? If I spread the sensor into the yield, how I can give referability to the unit of measurements? I cannot do the calibration. And the problem is not when the sensor doesn't work. Because if the sensor doesn't work, I have an information. It doesn't work. Okay. The problem is that when the sensor gives a number, but this number is far away from the true value. Or is a little bit, the uncertainty increased a little bit more. Because consider that when we have to evaluate something and the uncertainty on this measurement comes from the other measurements, and depending on the relationship so the measurement method that I'm developing, the a little bit increasing of one of the input of this model can become huge in the evaluation of the final uncertainty. So if we have not only modeling the measurand, but modeling the uncertainty, it can be a huge problem. And then there are standards that help me to give an answer to all these questions. So usually the tools, as metrological guys, the tools that we have is calibration and standardization and validation of the data. And as you can understand, these are paramounts for application of artificial intelligence. But artificial intelligence hide a huge problem. You use artificial intelligence, but you are not able to have the mathematical model. Otherwise, you prefer to have a closed information of what you are measuring. But we have no tools to evaluate the uncertainty when we use the artificial intelligence. I mean, when you are training an artificial network, neural network, you use the accuracy to stop the training. You use the accuracy to understand if the data set is suitable or not. But the accuracy, the tools, the computer scientist tools that have to evaluate the goodness of an artificial intelligence, for example, the false positive ratio, false negative ratio, sometimes, at least I'm saying sometimes, are not related with the measurement uncertainty. I have I have verified together with some of my colleagues who have worked on cells that we have tested this neural network UNet backbone with different backbones. If you use a traditional coefficient index to evaluate the accuracy, all these coefficients say the same things. It means that different backbones have the same behavior. But if you use the metrological definition of uncertainty, we have verified that two of them are very, very different with respect to the other. In particular, one is very, very good in order to minimize the maximum error, In this case, we can talk about error because we have a reference, the ground truth. And for us, it's the conventional true value. A conventional means that we take an agreement and we are agreed that this is the true value. The other ones gives the minimum average error. So as you can understand, also what you want changes what you have to apply. Further challenges and consideration, integration of technologies. In this case, you have to use standards, and standards compliance with measurements. We need to have energy efficiency, and the measurements, as you can see, is one of the most consuming energy and time in application. Data security and privacy, and this is fundamental to have trust among stakeholders. We have to manage data heterogeneity in terms of formats, structures, and units. And sometimes this makes the data not usable for training artificial intelligence network and so on. Scale discrepancies, temporal misalignment. This is a typical problem for measurements, synchronization. And in this case, coarse synchronization in time hide the dynamic relationship and dependencies between variables. And quality disparities, I mean different uncertainty, and how these different uncertainties in data will reflect on the final uncertainty. In other words, we need a deep knowledge of what we want to measure to assess the sustainability of precision agriculture. So, 2 forums I would like to share with you this information. My community organized this Congress, Metrology for Agriculture and Forestry, that for sure is very familiar for you. And the next edition will be in Padua. But consider that also yield, orchid are a building environment. So if you want to organize special session or you would like to enjoy with this conference, I'm warmly welcome to you in this year to Anja, Crete, and the next year will be in Venice. So I hope you will think about this. So in conclusions, few words. I mean that measurement serves all the technologies that we have saw in these days, but also I can say that robotics are opening unprecedented possibility for measurements, because now we can take measurements in place that were unthinkable before. So I hope that, and I would like again, Emanuele, that give us the opportunity to meet each other and to talk each other, and now we know what we are doing. So thank you very much. Some suggesting readings, and thank you for your attention.
Thank you for the presentation. So I don't know if you have questions. Better like this, yes. I don't know if you have any questions. Thank you again. So,
Thank you so much.
I don't know if we have
Yes,
to applause again, but no, anyway, so I think that
Thank you.
we can switch to the last speaker of this morning. So I will invite Luca Rossini to join us, and he will continue to speak on Pest for this session.
Okay, so can you hear me? Okay. So, thank you very much, and I am really glad to for all the interesting topics of these days, and I can say that the main topic is the multidisciplinary approach to solving this interesting problem. And so, in this session, we saw the problem of pest control. That is one of the most important things in agriculture, and above all about the on the cost, on the economical point of view, and above all on the sustainability of the production. And we talked about also measurements, but as the Professor Lamonaca said before me, so there are measurements, but there are also models. So that's why with my presentation I would like to introduce the problems and perspective of pest population modeling in agri-food. And talking about multidisciplinarity, I would like to introduce myself in a more entomological way, because I spent my egg stage studying physics, then my larval stage is studying agronomy, my pupa stage as a PhD in ecological modeling and applied entomology, and now I became a kind of young adult as a Marie Curie postdoctoral fellow in the control engineering and system analysis at ULB. So I like the jokes of my colleagues that define me as an insect guy who plays with numbers. But so talking about multidisciplinarity, it is really important if we want to cope the challenge of a rational pest control. So if we want to go towards a more quantitative pest control, we should take into account of all these fields and these disciplines. So we need entomology, we need applied mathematics, and we need control and automation. So this presentation is divided in 3 chapters where we will see which are the common practices in integrated pest management, even if they have been already introduced. Then we will go through the core of this presentation, that is the past and present of mathematical models, and then we will move towards future perspective, and I will explain which are our future goals. So this is a really simplified way of representing what is an integrated pest management process. So as Professor Contarini said before me, we have the farm that is our source of information and our final destination for the management. So we can collect some information from our farm through the monitoring activity that is the first ring of this chain, but we have seen that talking about measurements in agriculture and in pest control is something that is really expensive, and there is a huge problem. Then we would like to have a model, because based on the measurements, we would like to project the infestation and to know more about the future situation in our field. Then we have a decision, because based on the future scenario, the farmers can take more, let's say, weighted decisions. Then we pass to the control action, and the control action goes back to the field. So in this scheme, there are 2 dashed lines, because this is the process, and we will see that more or less is applied. But actually, those dashed lines represent a desiderata. So we would like, since monitoring is a high time-consuming operation, and you can imagine the cost of the measurements, we would like to optimize through the models the monitoring activity. So it's not just the data we collect from monitoring that support the estimation of the model, can help us to update the estimation of the model, but is also the other way around. So we may know where and when take measurements in our field. The second dashed lines, the second desiderata, is including the control action in the model. So if we are able to describe which are the control action and the most common control action with the model, we can simulate different scenarios. So based on the scenario that is more sustainable, so more environmental friendly, and that has the more reasonable cost, so there is also this balance to take into account, we can we can take the best decision. So this is an ideal world, but so which is the most common practice? So the problem is that in most of the cases, even if we are going towards an agriculture 4.0, 5.0, the problem is that the model is the farmer. So their experience is the model, because in most of the cases, they know which are the main pests for their crops, and more or less they are able to understand from where the infestation is coming, so basically the direction, and predict more or less which is the starting time, so at least to individuate the period. But it's not enough, because we are going towards precision agriculture, so we need to know exactly where and when the outbreaks are coming into the field. That's why we will go through all the ring of this chain, because our final goal is to try to reproduce with a mathematical model all this chain, so that the most important thing now is to understand which is the current state of the art of each ring of the chain and which are the open questions. So I'll go through monitoring, but you already know what is a monitoring from the presentation of Professor Contarini. So this is a measurements in entomology. So we have to go to the field. This is an inspection on a pest, the big bang mites that is infesting hazelnuts. So if you look at that, guys, those are the sensors. So it means that if you want to have a reasonable and a reliable information from our field, we have to spend a lot of time into the field to inspect a reasonable number of plants, but a reasonable, how big is this sample? So there are a lot of open questions, and the main problem is that measurements is something that is cost. So imagine that we have a big field. So we want to sample a large number of plants. How can we cope this challenge? We call more people. So this is the main problem in agriculture. So this is the case of visual inspection, but there is another technique that I would like to show that gives more the idea of how much time we need to do a measure, a single measurement. So, for example, this PhD researcher, Nicolò Di Sora, is doing what we call frappage. So, frappage is shaking the branch to monitor the stink bug, the Allomorpha alis, or other bugs that are infesting hazelnuts. And then, after the shaking, is counting how many individuals are falling on the white sheet. So, you have to repeat this operation for a reasonable large number of plants. But if we have 10 hectares, so we have to call many, many people. So this is the first problem. So we just started analyzing the first ring, and we already have seen some criticalities. But now let's go to the second chapter of this presentation, that is modeling. Because a model, by definition, is a simplified mathematical description of a natural phenomenon. And in our case, the natural phenomenon is an insect life cycle. So we should do, before going into the mathematical details, we should do an insect kit. So we should know what is an insect. And so we can recognize an insect as an animal with 6 legs. And we may have wings, but only in the adult stage. And we have 3 cases that depends on the order or group of insects. Then we have a pair of antennae, so 2 antennae. And we can always identify 3 segments in the body. So it is helpful from a modeling point of view. Not at all, but at least now we know and we define what is an insect. What is important is the second part of the insect kit, because we should know that insects are ectotherms. It means that the length of their life cycle strongly depends on the environmental conditions, so mainly on temperature. If we have very low and very high temperatures, the life cycle will be long. But for all the species, we can identify an optimal temperature where the life cycle is the shorter one. So this is an important point from the modeling point of view, but also from the pest management point of view. And also the second one, because the life cycle is divided in stages. So maybe you remember this joke I made at the beginning, but this is a simplified schematization of an insect life cycle. So we have egg, we have larva, pupa, and adult, but we can call the stages also in other ways depending on the order, but the concept is the life cycle is divided in stages. This is another important aspect. Also because in pest control, the stage is important, because depending on the control strategy we want to use, we have as a target a single stage. So imagine that the greatest portion of our pest population is in the adult field, but I am using a control action that has as a target the egg. I am just polluting the environment and wasting money, because the control strategy is not effective. So that's why with the model we should be able to describe accurately the population dynamics in each of the stages. So then another aspect is the insect population may be divided in sexes. So this depends on the species, but as we have seen, there is the case of the parthenogenesis, where females are just reproducing females. But before moving to the next slide, I would like to report a distinguishing mark, because I use always the word pest associated to insects. So not all the species are pest. We have more than 1 million of species, and if you just want an example, for all the pollinators. So they are insects, but they are not pests. So we don't want the pest in our field, but we want all the beneficial insects, because, for example, without pollinators, we don't harvest any fruit. No? So now we know what is an insect. We can move towards the mathematical description. And so an insect life cycle, we arrived to this very general scheme by analyzing at least 40 years of literature, because most of the models were introduced thinking about the special case. So there is an observation of the single case of study and then the mathematical translation. But if we analyze all the model, we can observe more or less that there are some recurring features. So our reasoning was, let's put all the recurring features, all the possible mechanisms we can find in the insect life cycle in a single scheme. So the fact is that this scheme is apparently nonsense. So if we propose this scheme to an entomologist, probably says, okay, there is nonsense. But the most important thing is that the biology should give us the hypothesis that we should translate in mathematics. So the most important thing is the biology. For example, if we remember our scheme, so each life stage from a mathematical point of view is represented by a compartment. So a compartment is characterized by a flux of individuals that are joining the stage, because they are passing from the previous stage to the stage we are observing, and two outcoming flows. So the first outcoming flows is the number of individuals that are passing towards the next stage. And the second one is the group of insects that over time are leaving the stage because they die. So we can repeat. And another important thing is that we have said that the length of the life cycle depends on the external environment. That's why we have some rate function that connect the biology of the species with the external environment. And this is one of the strengths of this scheme. Then we arrive to the last young stages, and we have the division. So our population is divided in two branches. A portion of the population will be adult male, and the second portion will be adult female. If we have cases of parthenogenesis, and this is true for all the parameters and the function that are and that identify some mechanism that this scheme is not describing, can be placed to 0. So in the adult females, we can have a subdivision because we can have different scenarios. For example, we can have species where the egg production of the female depends on the age. So young females produce a higher number of eggs. So that's why we have these 2 beta here. And for example, older females still produce eggs, but the quantity is lower. This is the case of some species of mosquito. Then we can have a second scenario that is more common, where the young female is still not ready to produce the eggs. So maybe she needs time to mate, or she still needs to finish the egg maturation process. That's why in that case, beta 2 is 0, and we have just a division in non-mated females and mated females. Then we can have cases of cyclicity, where a non-mated female is mating, lay the eggs, and comes back. So as you can see, if we know the biological traits, we can apply this scheme. So this was quite surprising because the quantitative data that we can get from the literature to parameterize the model is really low. And we chose as a first case of study the case of a very well-known pest for soft fruit cultivation, that is the Drosophila Suzuki, the spotted wing Drosophila, and where we had some data, some field data. So we parameterized the model based on the information we collected in the literature, and then we obtain this scheme. So as you can see, without any feedback from the experimental data, we were able at least to follow the trend. So this was a very first important result. But we still have a problem, because we said, okay, in precision agriculture, we should know where and when the infestation is coming. So with this model, we potentially answer to the question when. So, but we should take into account that insects move. So we should be able to describe also the spatial diffusion of the insect in our field. We try to approach to this second problem by adding some assumptions. And that's why, again, we step back to the biology, and then we try to translate to mathematics. So if we think about the stage division of the insects, so we can identify some stages that are where the mobility is strongly reduced. For example, an egg. An egg is forced to stay in the place where it has been laid, while an adult can fly for long distances. So if we include, if we consider this additional option, the assumption, and we divide our field in a grid, we can describe each subparcel with the punctual model we saw previously. And then we can make the assumption that two parcels in this scheme can exchange individuals of the mobile stage only if they share a side. So this scenario. So now with this scheme, we at least formulated a theoretical framework that can potentially answer to the problem of insect motion. And unfortunately, it's still just a theoretical work because as we have seen, the problem of monitoring is one of the strongest limitations. So for validating this data, this model, we need a huge amount of data and also with a kind of good resolution. But we hope to have it in future. But there is still a problem because so if we want to solve a model, we need to know which is the time zero of the infestation and which is the initial abundance of the population. So basically, we need to estimate the initial conditions. But talking about the monitoring activity, so it's not easy to find, so to estimate the initial condition in a very accurate way. That's why we go back to our scheme, and if you look at the title, it's changed in what we are going to do. So we are moving towards the future perspective and what the future is, which are the future activities. But if you remember the first time I presented this scheme, there were two dashed lines. So the third part of this presentation will be on the dashed line because they represent the future perspective. So all these open questions that we had during the theoretical development and the various applications led us to formulate, to write a project proposal. So the project proposal is the project Pest Finder that is funded from the European Commission and is a Marie Curie postdoctoral project. So the project is supervised by Professor Garone and led me to the department to control engineering and system analysis because it's the last ring of the chain to complete to improve the theoretical scheme. So the project has three objectives mainly. The first one is improving the model. So we can always improve in the model because by definition it's a simplified description of phenomenon, so it means that we can always add some aspects to improve the model. The second objective is the optimal measurements, planning, and estimation. So basically what we can do is to use the models to optimize also the monitoring. So we want to see, we want to have an idea of where and when we have to measure. The third objective is basically closing the loop of the IPM. So we want to include also the control action in the model, and we want to be able to provide the different scenarios in order to take the best decision for the pest control. So we have time because the project started in October 2023, and I mean, it's a very highly multidisciplinary project. That's why we have the support of different groups. For example, the group of entomology of the Professor Francis, or my former colleagues in Tuscia, the entomology group of Professor Speranza. But it is also important the feedback of the producers. So this is an aspect that emerged yesterday from the presentation, and having a feedback from who will be the final user of this kind of systems is important for us to understand which is the most important direction that we have to take. So the project is just started, but we have some preliminary results, because if you remember, the last problem we left was the initial condition. So we were able just to run the simulations by assigning some random initial conditions. The problem is that we can have some monitoring data. It's true that there are some problems in the monitoring, and these are time-consuming operation. But if we have some data, why we cannot use them? It is what we did, because basically we applied a very well-known technique for engineers, but in a very different field. So, for example, from the entomological point of view, what is an extended Kalman filter is completely unknown. But it's a two-step algorithm with a prediction we entrust to the model, and then a correction, because we are using the data. Every time we have a data, we correct the estimation of the model. And we are reducing the dependence on the initial condition. So here we have the simulation without any feedback from the field data, so there is a higher variability in the simulation. But here, if we apply the extended Kalman filter, if the data becomes an active part of the system, we are in some way solving the problem. And also the trend of the simulation follows a bit better the experimental data. So this is just to see that we are going towards a more quantitative description of pest populations and of pest control. And this is important. To do this is important the multidisciplinary approach. So the interaction within different fields, and we have to talk each other. So finding a common language. And besides the scientific work, we also realized to have a mission, because while in most of the field, in other fields of research, the data collection and data sharing is well regulated, this is not the case at all of entomology. So we want to promote also the data collection and sharing, and also the way, so a standard way to collect the data, because we realize that is one of the most important things in research in entomology. So thank you very much, and if there are questions, you are welcome.
Thanks a lot for the presentation. So is there any comment or questions?
Probably a couple of questions.
Yep.
So first of all, I was wondering, since everything, I guess, and you emphasized, is quite complex, also in terms of regions where these insects could spread. So I guess you are using ordinary differential equation to model each dynamics.
Yeah.
I was wondering if why not using, for instance, a stochastic approach to define the model in linking to each place the probability of finding a certain insect and not the number of insect itself. That maybe is a bit harder to be identified. So this is the one question. The second question, I told you all the three that I have in mind. The second one is, according to your experience, you're using extended Kalman filter. So I guess that the phenomena that there are behind are strongly nonlinear. So linear approximation in describing the dynamics is somehow reliable, or indeed a truly nonlinear approach should be adopted in certain cases. Third question, and then I stopped. Kalman. So you adapt the model, or you adapt the estimation So the model is fixed, and somehow you try to adapt the guess of the estimation provided by the Kalman filter, or using some kind of adaptive control.
So the problem, to answer to the last question, is that actually we don't know which is the uncertainty on our model and on our measurements. So what we did is a very rough estimation of an uncertainty based. We should explain how to estimate the parameters in the models. So basically, there are experiments where insects are placed in climatic chambers, and the lives at fixed temperature, and the life cycle of each individual should be followed till the end. So we repeat this kind of reading for different constant temperature, and then we get this data. So we do an interpolation. So there are empirical functions that should relate more or less the biology of the species with the thermal response, so the external environment. What we can do is just considering a kind of uncertainty that comes from this fit. So this is the way we estimate in the errors. About the possibility of considering stochastic equation, right? Maybe can be an option. So I don't know, but maybe we can see in future. So the problem is that if we don't have accurate data, while for the punctual model we can use some data. So for example, monitoring on a portion of the field, or for example considering the information that comes from more traps. So we are still not able to do it for the spatialized model. So maybe yes, maybe no, but for sure we have to consider this aspect. So I hope to have answered to all the questions. Yeah.
Okay, is there any last question?
Thank you for your presentation, Frederic. Did you try, so I understand you use a non-linear approach for identification.
Kind of.
So did you try a locally linear approach? So breaking some ranges, in locally linear paths?
No. What? The model is linear. Yeah. So because the model is linear but becomes non-linear because of the uncertainty we estimate. So this is the main problem. So for sure we have to improve the models. So this can be an option for the future. But so if we think about the model is linear. The problem is that it becomes non-linear because we have to make all these those additional assumptions to try to estimate the error. So it's a kind of loop. So the problem of monitoring is in some way influencing the problem of modeling, and the other way around. That's why we have to work from different aspects to. If we want to have a more precise model, we have to improve the data collection and measurements, for sure.
Okay, so thank you again, Luca, and the two other speakers of this session. And now I think that it's time for the lunch and the break.
Thank you. Okay. Okay, so let's start with this last session of this two-day forum. And so here we will. We have understood that the the biology is the final destination for robotics, but here with this session we want to explore if the biology can be a source of inspiration for robotics. And so we will have 4 speakers, and the first one you know very well who is. So it's our general chair and one of the co-director of this season BrIAS, Emanuele Garone. So professor of control engineering at 12B, but I leave you the floor.
Okay, so first of all, thank you, Luca, for introducing me. And I promise you one thing. Originally, I didn't foresee to speak because I was thinking you had already to see me way too much time. But I wanted Nicola Bonorossello, that is one of our former PhD students who now is doing a postdoc in Namur, to present these results. But unfortunately, a few weeks ago, I come to know that Nico could not be present because he's teaching in Namur, so I had to take over. So please forgive me if you have to listen to my very pleasant voice for again, like if it was not enough for the next 30 minutes or so. So here we want to speak a little bit about the problem of active monitoring, of path planning, and of models, and how these things mix with the goal of precision agriculture. So let's start with one thing. So very often in these days, we have heard about the need to monitoring. Now, I have seen several definitions of monitoring. Just to be clear, I imagine that all of us, when we say monitoring, we don't care just about collecting data, but doing a little bit more than that. I mean, if my wife, who's here and is present, tells me that I have to monitor the kids, she doesn't want me to take data on a piece of paper. What she wants is that I maintain a surveillance on what's going on. So at the minimum that they don't do something stupid, they often do. They don't do something dangerous, sometimes they do, and so on. Now, this, just to be clear of what we need by monitoring. We just don't want to collect data. We want to do something with that. We want to see what's going on in our system. Now, in the industrial setting, there are difficulties like anywhere, but monitoring is relatively simple, because what we do is that we put sensors. In many industrial settings, we have restricted areas, so the plants are not enormous. You put the sensors in the various places. It can be more or less expensive, but it's doable. And then what we do with our sensors is we check. We collect the data with the goal of checking that everything is okay. For instance, in this case, that the level, what is the level of a tank, and the level is not above a certain threshold. So this is what we do naturally. And when we speak about spatially distributed environments, one can think I would like to do the same. But there is a problem. When we have a spatially distributed environment that cannot be just agriculture, but also think about cities, but of course, even agriculture, well, we would like to do the same. We would like to collect information to understand what's going on in such a way that then we can make action, we can make monitoring, and so on. So this was the starting point of a project that I'm sorry you had to hear about it multiple times, because somehow it really shocked in the deep, heart in the deep, or inspired in the deep many of us. That was this project in which we had this idea of doing what in the industry is called a SCADA, so a supervisory control and data acquisition system, to do the equivalent for agriculture of this. And this, the starting idea is we need to use sensors, and we might put some sensor on the field, but immediately we understood that sensors had to be mobile, and they could be drones, they could be ground robot, they could be, as we have seen before with Luca, people like Luca that go around and make the measurement in the field. So this is what we started doing. I like to show this video where there is me piloting this drone in our orchard. Please note the wonderful hat. So this is what we were doing. But while we started doing this, we realized that there is a fundamental limitation that it's there, whoever is in the field can see it, but was not so much understood. And the fundamental limitation is that if we look at how we collect data, and this is from an autopilot that our friend Paolo Marras knows quite well because it's his system, or I can take other commercial ones. When we collect data with the drone, but also with the ground robot, what we tend to do are this kind of trajectories. So we have so-called lawn mower, or if you like, Greek boustrophédon trajectories, where you go back and forth, and you collect data everywhere. This is the classical approach that is used also in other applications, like in geographical surveying, in photogrammetry for buildings, for cities, and whatever else. What is the problem of this? Well, the problem of this kind of approach is that it is inefficient. So you are trying to measure everything, and if you are trying to measure everything, there are times in which the time that you need to complete the mission is too high. Now, consider this little thing. This is actually from a real flight plan that we had in our field, and we could cover not even 1 hectare in 34 theoretical minutes. I'm saying theoretical because in reality the battery here would last 20. So to cover less than 1 hectare, we needed 2 sets of batteries. Of course, here we were flying at a low altitude, so it was a little bit of a complex situation. But if you consider that this farm, if I remember well, it's around 120 hectares in total, try to go to the farmer and say, well, you know what? If you want to scan and get information of all the trees in your field, you need this by 120, so 60 hours, and you will scan everything. Without considering the time for takeoff, landing, changing the batteries, charging the batteries, and so on. It is, of course, something that we can do as academics to write a paper, maybe to write a well-cited paper, but that's it. But anyway, I must say that, of course, at different altitude, you can do much better, and then it becomes more convenient. But this highlights one thing. Here we are trying to collect everything. We are trying to do this monitoring. But are we using the right monitoring strategy? Are we really collecting all the information it's needed? Wouldn't it be much better to have a monitoring planning where we try to decide what we need to measure and when, not to try to measure everything, but to measure what is relevant? Stupid example. My wife asked me to check on the kids. I know that first thing that is super relevant is that they don't hurt themselves. Second thing that is most relevant is that they don't destroy anything, and so on. So, of course, not all information have the same value, and not sampling everywhere might have the same value. And anyway, in most of the cases, simply you don't have the resources to monitor everything. So one thing that we realized is that when we are doing monitoring in distributed environments, so in large environments where we are using mobile sensors, the reality is that we have a limited capability to measure. Maybe we can measure half of the parcels. Maybe we can measure less than half of the parcels. So this, if you want, it's a little bit against the spirit of precision agriculture we were saying yesterday and today. So precision agriculture, we want to know, if we are speaking of trees at the level of the single tree, what is the status of the plant. Now I'm telling you that it's impossible to measure all of them. So we could say, okay, it is not realistically convenient to monitor all the plants. We would like to monitor all the plants. Then monitoring all the plants, it's economically not convenient. It's a nice academic exercise, end of the story. Well, this would be true if we had no knowledge concerning the plants or concerning the system that we are measuring. But the reality, it's a little bit different. Why the reality is a little bit different? Well, there is a first mitigation aspect. Very often we have other sensors, and this might help, and then this might tell me, okay, at least I go to measure where I have really no information rather than measuring where there is already a fixed sensor. So this is nice, but does not really solve the problem. However, there is another source of information that is very often not really understood. That is the fact that if you know something about the nature of a phenomenon, then you have a valuable information that you can use to complement your measures. In other words, everything can be recovered if we have models. And this is the reason why, and to this I link to the previous intervention, it is important that we develop models, possibly models that we can understand, because they allow us to fill the gaps between what we measure and what we estimate. They allow us to make estimations on the basis of measurements that are not the measurements of everything. So this is the starting point of our, was the starting point of our research in this field. That mentally it's to pass to the idea that what we do is to collect data, collect all the data, and then processing them without exploiting a priori knowledge on the system. Vice versa, we believe that an approach that is more viable is to have that the data collection and the data processing are two intertwined aspects. And so what you measure depends on how you process the data, and you have to consider the two together. The main aspect of this idea is, first of all, to know and exploit a priori knowledge of the phenomena. In agriculture, this is very often easy. Why? I mean, not that you are a good model, but there are things you can say. So, for instance, there are temporal aspects. If I flew yesterday on a plant, and yesterday the plant was infested, or it had a problem of water, and if I fly the day after on the very same plant, very likely it will be still infested, or it will still have problems of water. So there is a temporal correlation in our in what we measure. It's not that it's completely unknown. And very often there is also a spatial correlation. So very likely, if a tree has a problem of drought, if it has not enough water, very likely the trees on the same line just close to it have the same problem. And so what is important is to try to exploit this data, it's not data, this knowledge, and cope with the fact that you have a limited sensing capability, and try to optimize where you can put your sensing resources, trying to optimize some indicator of the quality of your estimation. Now, this is very general, and there is also quite general methodology to try to cope with it. that it's basically based on 3 main steps. The first, modeling of your process. So try to have a model that tells something about what to measure and when. The second thing is to choose a way to estimate what you want to estimate. And what is important is that beside deciding how to estimate, it is very important if you can define an indicator of how good is your estimation. So something that, and here I connect with what Francesco was saying, is an index related with the uncertainty of my estimation. Because uncertainty is not only for the measurement, it's also for the estimation. So you have the reality, you have what you measure that are some of the variables that are a part of the reality, and then there is what you estimate, that is all the variables that you want to estimate, also those that you don't measure but that you can infer. And then once you have done this, what you can do is, among the possible sampling that I can do, you can select what is the one that optimizes you can select a strategy, it is the one that optimizes your index. In particular, for instance, in the case of a drone, you can do a path planning that minimizes the uncertainty of the estimation of what you get. Now, this is very general and can be applied to various types of systems, both classical dynamic systems or systems that are driven by stochastic equations. I will show you a simple case study that is the first that we did on linear time invariant processes. That it's one, I think, of also the most useful, at least for when we speak about differential equation models. So we start with this case of an LTI process. We have understood that these are the 3 things we have to do. Let's start with the first. What is the model? Well, I consider it as a case, an agricultural setting where I suppose I divide my field in small parcels that I describe as a graph. And I assume that to each of these parcels, there is associated a dynamics. There is also a coupling dynamics between them. And there is an uncertainty due to the model uncertainty. Again, link with the uncertainty. The model itself has a certain reliability. Now, normally we don't know how much it is, but grosso modo we can make some estimation. We can say it's big, it's small, it's completely crap, it's relatively precise. So this is the dynamic of the system. It's our model of the system. We also need a model of our measurements. And typically, we are in a linear time invariant system. We can assume that the sensing structure is just linear. And we can distinguish between sensors that are fixed and sensors that are mobile. Now, this is a little bit of mathematical trickery, but the sensors that are fixed, you measure every single time. The sensors that are mobile are modeled in the following strange way. Now, don't be too scared. I just assume that there is a sensor for each parcel, and then I put a variable gamma k that is 1 if that's a parcel that I visit in my flight, and 0 if it's not. What it ends up, a little bit of mathematics, but please don't be too scared, it's an output that is linear in my variables, and where I have this matrix that is composed of all these vectors, sorry, of all these scalars, gamma k, that it's a way to select which are the parcels that are visited during my flight. So this is just a time varying output where also the dimension of the output can change. It's just a standard way to write it. Don't worry too much. Just think I have outputs parameterized in such a way in which with 0 or 1 I select in which parcels I pass or not. And I have an uncertainty, again, linked with my measurement. Okay, this is the setting that I established. So this is just a simple linear system with a time-varying sensing structure where I have some decision variable 0, 1, depending on what I decide to measure or not. With this, the first step of my methodology is done. So I am okay. Next step, I can do the estimation. Now, I will not go too much in the detail, but we are in a linear system. We can choose the optimal estimator. What is the optimal estimator is the Kalman filter. Kalman filter, what it is, it's something that does actually prediction based on a model, correction based on the measurements, and mediates between the information coming from the model and information coming from the reality to make a prediction that can be proved it's optimal. Here are the equations if you want to enjoy with the equation. These are very standard equations. You can find them even on your Wikipedia page. The only thing that will change are all these gamma that represents these choices 0, 1. Now, one nice thing about the Kalman filter is that beside being optimal, it's also the fact that we have this matrix pk plus 1 given k plus 1 that is the matrix of the covariance of my estimation. So again, it's a matrix that tells me something about how good is my estimation. And so what I can do, I can use this matrix or some index based on this matrix to find an index that I could minimize. Now, we could do so, but actually it's not very convenient. It's much better to use the inverse of this matrix, that is the so-called information matrix. This is just for a reason that is a bit subtle, but if you do so, these variables that are 0, 1 become linear. And so they are much easier to be treated. And now if I decide to use this matrix, I can define an index based on that. There are values. There is D optimality, optimality, A optimality, means various things. In our test, we have seen that in practice, the most convenient for the information matrix is the E optimality that maximizes the smallest eigenvalue of the information matrix. So we decided then for this that can be rewritten then as this criterion for the optimization problem we want to solve. And at this point, we could say we have solved the estimation part. We have said how to make the estimation, how to evaluate how good is the estimation if I do a certain selection of the parcels that I visit. At this point, there is the last part. I have a model. I know where I can go. I know, depending on where I go, how good is my estimation. Let's try to find the best path that minimizes so that makes my performance as well as possible. In this case, it was maximizing my performance cost. So how do we do that? Again, a little bit of mathematics, but what is the idea? The idea here is that we were thinking about a drone with a limited autonomy, so a limited amount of time it could stay on air. And we considered the various measurement points as a graph you can pass from one to the adjacent parcel and so on. And if we want to minimize this cost function, maximize in this case, this performance function that we have seen before, while selecting path in this graph, this problem is a so-called orienteering problem. Now, what is an orienteering problem? It's a problem where you have a graph and you want to select which nodes you visit and in which order. It's a problem that is nasty, but not so nasty. So it's a problem that can be written in this nice way that can be proved being NP-hard. And in particular, it can be proved to be a mixed integer semi-definite programming problem. It's an hard problem. It can be proved to be hard, but it's still something that under some limited assumption we can solve. So what we did is to solve this problem for a few cases, and we got a few interesting results. So first interesting result, we wanted to see how the distribution changes if I change the fixed sensor. And as you can see, the trajectory tends to avoid where there are the fixed sensors, because the fixed sensor already gives some information. Much better to sample far away. Very logical. Another interesting thing was to do some sequential, so to see, because here what is the input? It's not only where are the sensors, but also what is the quality of my previous estimation. And so the new estimation depends on how good was the quality of the previous estimation, and so also the path depends on that. And so you see that in the first passage where the covariance matrix we put was very big, we had more or less this kind of diagonal search that is 90 degrees, so orthogonal to where I placed all the sensor. And at the next step, it will be something that kind of goes away from it. It goes from another path. So at each instant, it will go for different paths depending on what happened before. A little particular, this is, when I saw this was very nice because many years ago I asked Stefano, that was here, how do you sample which plants you go and check in your plantation? And he told me, I go diagonally. So when I saw this, I was feeling particularly happy. Okay, with this we could say the problem is solved. In reality, it's not, because this optimization problem is quite heavy. Just to give you an idea, if I consider a parcel 4x4, it's 8 seconds, 5x5, it's 170, 5x6 is 370, 6x6 is 1 hour, 7x7, probably it's some month. If you go a little bit higher, this is what you will have. So unfortunately, this is a problem that does not scale well. Then what we did is to say, okay, it's a problem that for large instances, it's impossible to solve exactly. We went for heuristics. Now, I'll not go in the details, but what you do as a heuristic is basically, the idea is that rather than selecting a direction, you select the probability to go in a certain direction. We built some heuristics, and we show that at least for the cases we could compare exactly the performance, the degradation was limited, but as the number of points increased, instead of having an explosion, we had something more decent. Okay, now the question is, does it work? Well, to see if it worked, we considered a almost real case. We didn't have enough data to do a real case, but we used some synthetic data on a possible experiment on irrigation. So we had a model that was modeling the water distribution in an orchard. So the fact that water may flow from one parcel to another, that there is a spatial distribution, et cetera, et cetera. We considered some uncertainty of so some process disturbance and some measurement noise, and we considered a mobile sensor that had some sense. In particular, these are the data of kind of a decent drone, and thing that might seem strange, a sampling time that we did not know a priori, because that's something that happens very often in the field, that you don't know when is the next time you will really go in the field, because that next day it might rain, it might be not a good day, and so on. And these are the results we obtained. Now, to try to have a fair comparison, we compared our method with the classical method of doing a bootstrap-fadon, but with the resources we had. And what we can get, so this is the performance index that we are maximizing. You can see that our path planning based on the information matrix works always better. And very interestingly, also if we look at the trace of the covariance, that is not something that we are minimizing, but it's an indirect thing, it's still much better. So what are the conclusions of my talk? Well, the conclusion is that there is a bad news. In agriculture, we cannot measure everything. It's not me that is giving you the information. All the speakers have basically pointed at this. The good news is that since agricultural systems are dynamic systems, they can be modeled, and the model is an extra, if you want, virtual sensor for us. It's something that gives us information that we should not throw away. And my conclusions is that then using estimators plus ad hoc planning can still allow us to estimate with a good uncertainty the state of our agronomical system. Now, if you want a reference for what I've shown to you, this is probably the paper where we have written it in a decent way. And I also want to mention that the main author of this paper, that is Nico, that at the time was a PhD with me, with the preliminary work that he did for this paper, got actually 2 international prizes, actually went twice to the Agricultural Conference and got Best Student Paper 1 year, and then 3 years after, at the next edition, got again the Best Student Paper, and it was all the basis for this. Now, what are future works? Because this is, of course, just LTI systems, just the beginning. For sure, better heuristics. Another thing that one could say is that here I'm using a myopic approach. So I'm just trying to improve the performance in one step. What if instead of planning just the next mission, I can plan the next season of mission? Things might change. Nevertheless, you have to take into account that we went for a myopic exactly because in agriculture you don't know when it's the next time you can sample. Other very interesting case is the nonlinear case, because here I am actually tricking you a little bit, because I'm saying that I'm closing the loop between the data that I elaborate and the planning, but in the linear case, the quality of the information is independent from the information itself. If you go in the nonlinear case, things are much more intertwined and much more interesting, in my opinion, but also much harder. Another case that we were studying, here we had some initial results, was on multiple vehicles. And there is another case that is not anymore really future work, but let's say for agriculture it is also the case of going for discrete event systems, and in particular for stochastic systems, for instance, Markov chain, because there you can use exactly the same ideas, but you cannot use the same methods. In particular, there is a problem of what is the estimator. Now, we worked on this, but I must say that while we were trying to applying it in agriculture, there was another emergency going around in the world, and we realized that we could use it for the problem of smart testing in COVID. And as a matter of marketing, we prefer to do the paper on COVID rather than the paper on agriculture. But in reality, the mathematics behind would be exactly the same. So with this, I conclude here my presentation. Thank you for having patience with me and with my voice yet for another time. Thank you.
Thank you. So there are questions from Slido. There are no questions from the audience. Any questions?
Well, you don't want them?
No,
Come
no.
on. They have listened to me so much.
Okay. So.
Oh, there is one there. And now I am afraid because.
Actually, it's really interesting, really nice. I liked it. So when you talk about this LTI system, you have a system that depends only on time.
Yes.
Is it possible to imagine something that depends also on space? Because, I mean, as you said, X at position
yes.
K, Z, I don't know how to call it, depends on X on position Z plus 1. So some spatial dependency.
In reality, there is a spatial dependency.
There is.
It's probably I didn't say it well, but let me see. For instance, here you see that there is an A. It's not x k plus 1 I equal to A x. In reality, A it can be whatever matrix.
Okay, so it could be.
Yes. So actually, in this model, for instance, there is. In fact, you see the arrows here. We consider from one parcel to the other, there is the water that can flow. So if you have an high humidity in one parcel and the low humidity in the other, you have this transportation phenomenon.
Yeah. Thank you.
Thank you to you.
Okay. Other questions? If not, we move to the next speaker. I invite Brand Timmons on the stage. And Bram is the CEO and co-founder of Pats Indoor, and is a company that automates insect control from greenhouse and using vision and micro drones. So I am really curious to see how to manage pest control in a very innovative way. And okay. No problem. I have a good reason now. But
because this 7% is going to take...
okay.
You always see it. If that's okay.
Okay, okay. Okay, Matei. Or maybe, but no, you have your presentation on your computer, yeah.
Give an introduction, so that will probably help, but I'm not sure if this people can now follow how my update is going. Well,
better? Yeah, okay. We're almost there. So sorry for the keeping you up. My name is Bram. I'm one of the co-founders of Pats. We're a Dutch company. We're located in Delft, and we're a spin-off from the technical university. I myself have no technical background. I'm not a researcher, so today will be mainly about practical applications. And of course, my co-founders and the people that work at Pats, they have a background in engineering, control, vision, agriculture, biology. So we are well represented in that way. Don't worry. What I want to talk about today is that where are we today, but more first to start with, how did we get there? Because when we started Pats, we started a little bit with a crazy idea. We had the idea to kill annoying mosquitoes in summer that keep you awake, to kill them with little drones. Actually, Matei is from the same drone lab, so he knows about the whole journey from my co-founders and the crazy things they are thinking about. Next, of course, to drones serving beer, also a very actual problem that we need to solve. But that is crazy idea with very cheap drones from China. Okay, can we kill those mosquitoes with little drones? So what did they do? And I'm going to show a very cool video in a little bit. What did they do? They went to the swamp, catch some insects, some mosquitoes, left them alone in a room like this, a little bit easier to find them, and started flying around with little drones and a controller after the mosquito. And then the moment they came close, they're like, okay, what happened? You know, and once more, once again. So at some point they thought, okay, now we have to really look what's going on. So they put a high-speed camera on it. They took one little drone rotor, a bulb, and then just patiently wait and throw in a mosquito when the engine the propeller was turning around. And the really cool thing is, and you're going to see it in the video, I hope in 6% from now, which always takes the longest. yeah, you see the insect from close up, smash, and get killed. It's very cool. It's very, very visual as well. But, and of course, we started to think, okay, how can we use this? Yeah, because, yeah, okay, it's cool for mosquitoes that are, what do I call it, carrying diseases. Like Zika was a thing, because this is 7 years ago. You have malaria, of course. That's quite some challenges there. Then, at that moment, at some point, we thought, okay, so we are using small drones. We are using the easiest drones, so we need to control them externally. We need something to see the insect, to see the drone, and bring it together. If we're going to do that in a bedroom, we're in a different domain. Cameras in your bedroom is not a very good idea. So we are in Delft, and I'm not sure where you are, if you know where that is in the Netherlands, but we are, let's say, encapsulated by greenhouses. You have the Westland area. I think there's 3,500 of just glass greenhouses. You're going to drive there, you will not see anything else than glass, and that was where we are. And then some people, well, we had no background in that domain, started to point out, okay, maybe you have to take a look at horticulture, at greenhouses. They have quite some big challenges there. It goes for horticulture, it goes for agriculture, with, let's say, the shift moving away from, let me try to get this thing up and running, moving away from pesticides that are being more and more regulated, with the Green Deal coming along. Well, okay, that one is off the table for now, but it will definitely come back. So that was that was the thing that we started to investigate, and then we learned at some point that those pests are a big problem, and there are actually quite some pests that are really hard to control and that mess up the system that growers have. We call it integrated pest management, where we use biology to control pests and then only do corrective measures when needed. But of course, that is a very, let's say, unhappy marriage, because I mean, if you're trying to deploy little parasitic wasps, killing other insects, and then you have a big caterpillar munching its way around, and you spray that caterpillar, you definitely will also kill all the other insects, the bad ones, but also the good ones. So there goes your investment. So, let's go here. So, we did this crazy idea, I showed them a little bit. We did that in 2016. That became a company, a commercial company in 2018, and has been evolving. And I want to take you on that path. So where are we today, and where are we going? Where do we think we can go with this? What kind of impact can we make? Because that's very, very important for us down the line. So I want to show you a little bit about that. Let's now get to the visuals, because that's what you all have been waiting for, probably. You know the problem. So we come back to that. You see the greenhouse. Well, this is what you all wanted to see, of course. This is a very tiny mosquito. This propeller is, let's say, 2 centimeters wide in, come on, Windows. 2 centimeters wide in size. Insect gets kind of sucked into the system and then, well, smashed to pieces. Well, it's a successful elimination. This one is pretty obvious, easy to measure. There are a lot of pest insects. I don't have to explain you all. They're very small ones, they're very big ones. There are good solutions for some, let's say sustainable solutions, but for some it's very tricky, and like I mentioned just now, they're messing up the system. And one of those insects that we started to target are caterpillars. Caterpillars, well, you probably all read, if you have kids, you have read the very hungry caterpillar. They eat a lot and they eat fast, and if you are not paying attention, things can go sideways really fast. Come on, next slide. Oh, can go sideways very fast. So we started to focus on that insect. The caterpillars in horticulture are mainly distributed by moth, so the night-active butterflies. They suddenly come inside the greenhouse, or they survive after winter time. The temperatures, the biorhythm becomes favorable, and they start to spread like crazy. It starts small, like everything, but in the end it's just like, yeah, an exponential growth if you cannot stop or control it. So we first started in the flowers. You don't see the flowers here, but we were in many greenhouses. And you have to see, we have these engineers who really like to build cool stuff. And we're just like, yeah, in herbs, in potted plants, in vegetables, wherever we could get in, we were testing around and doing our stuff. And that meant that we were sitting there often at night until very late. Sometimes successfully, sometimes less successfully, but we started to develop this system that we devised. A little drone system, autonomous drone system, very simple drones, nothing special. We took everything off the, let's say, FPV racing drones, for example, and control it externally. So to put the intelligence outside the drone to make things manageable, and with some thought about after it, behind it. So the thing that we thought of was like, okay, in a greenhouse, you have a pest, it starts to develop, and then becomes a problem, and then we start to do corrective measurements. Our goal was to take out the first, or let's say, the first few instances of an insect before they started to developing. And it can be from inside the greenhouse or from outside. That is, of course, not easy, so we spend a lot of time doing that. That resulted eventually, and it's still in development, to be honest, but it's running at some trial sites, that resulted in our drone system. You see the drone here on a charging platform to make sure it's kind of autonomous. But all the magic, this is a tropical plant nursery, all the magic happens in that box. So this box, which has an infrared camera, we support it with infrared to see in the dark, to see those night active insects, otherwise the system would also be blind, is seeing a lot of movement through the greenhouse. Based on what we see, we start to label insects and in real time to determine between the bad and the beneficial insects, and then also to narrow it down and say, okay, what actually insect are we looking at, and how are we gonna chase after it and eradicate it. Maybe start with a little demo just to give a little bit of idea how that works. Here my colleague, this is by daylight. I also have some examples with successful kills from the greenhouse actually. Here my colleague is throwing out some bubbles. Just to understand the principle, the system sees those bubbles as bad, as multiple insect, goes after it and takes them out. Well, bubbles are easy to smash, of course, but the same goes for insects. They are often very, let's say, soft material, easy to chop, is that the right word? To take them out. Goes back, recharges. So how does that look like in a greenhouse? At night, so you have to look a little bit, squeeze your eyes maybe, because we have only grayscale images because it's in the middle of night. Thank you very much. You see the plants here. Here's the drone system, sitting on the drone on the pad, just patiently waiting until an insect passes by. And then on the right side, so you will see a little indicator come in. That's the insect. On the right side, we do some filtering to see the movement, because otherwise it's really hard to track it. Let's see. Yeah, you see the indicator come there, but on the right side you can actually see the moth, and the drone starts to chase it, and then Pots makes moth confetti, as we call it. And it goes really fast. This is, let's say, we see it and we take it out in under 2 seconds and eradicate it. Now, when we were building this, we also had the thought of, we know it's a big problem. It's a really hard to tackle problem. Whatever moth or caterpillar you're looking at in horticulture, it's one of the most challenging pests, especially with the possibilities growers have. And we thought, okay, they're nice and big, so they're easy to see. We were right on that. They fly in the night, so it's safe to fly around the drones before we have, let's say, a safety net to avoid humans or to not fly at humans, so that we were right about that. And they're easy to catch. We weren't right about that. So we were wrong, very wrong. I mean, in this case, not so much, but some moths really see our drones as a predator apparently coming after them. So they, of course, I mean, there's like an, they call it evolutionary battle between, for example, bats and the moth flying outside and trying to survive both, one by eating the other, the one by evading the other. And we noticed that as well. And that is pretty annoying, of course, but also pretty cool because we got some new ideas because of that, but I'll come to that. We are developing this system. Let's go to the next. There's some problems after the pictures. We're developing this system, and we were sitting in flower greenhouses. And we typically went there, let's say, around 6. Then they darken the greenhouse. That's what the plants need, so that was nice. But they darken the greenhouse, and some nights, the moment the greenhouse was dark, just the cloths closed, all the moths started to fly around, and sometimes even clapping to your face, and very nice experience. But they were all there, and it's very nice because you're live iterating on the spot. But some nights we're sitting there until 2, 3 in the night, and we're like, okay, this is annoying. We have seen one moth last night. That was not really a good testing night. How can we solve this? Because yeah, you're engineers, you can do it once, maybe twice, but then they say, okay, yeah, I also have wife and children, or I have a life, so we cannot continue doing this. So we decided, okay, let's put some cameras in greenhouses. So they all had the same problem. The cooperative that we were working with, about 50 growers of gerbera daisies, the flowers, were quite excited about it. So they gave us access to greenhouses to put camera boxes there. It's just the same camera that we would later use to control the drone. And we were coming out of winter, so it was quite slow. So we're just waiting, and in the morning, people were going through, let's say, raw video footage to see, is there anything that looks like a butterfly flying around? So really the boring work, but yeah, that's part of it. And at some point, we see some moth flying. Okay, we need to talk to this grower and try to get access to this greenhouse. So we called this grower, and we said, hey, we see that there's quite some moth in your greenhouse. Can we come the coming nights and have access, because we know we're there, we're not coming for nothing. Yeah, that's nice, pretty cool, I'm pretty excited about it. Here's the code of the door, go in, and maybe I'll check out myself, but go ahead. And before he hung up, he said, but I have one more question. How do you know we have moth? Yeah, well, we see them flying, but you don't, because you have traps to catch them, UV traps they use. You have pheromone traps, so that's the female sex pheromone, where the males are attracted to. They are very eager in scouting for caterpillar damage or egg deposition. There's people going through the crops every week, sometimes multiple times, and you haven't seen anything. No. Okay, we just do the test. 2 days later, one of the other growers calls me. I think it was 5:30 in the morning. I was still sleeping, hadn't had kids yet then. And then he said, I heard that you can see moth on this camera. From this other grower, I have a camera. I want the data as well. Yeah, we don't have data. We're going to raw footage. A whole discussion, and then he said, well, you better make data. Okay, we want to make this control system, you know, so okay, let's do it. And because the whole collective, growers, consultants in crop protection, cultivation, they all started to get involved, to have a discussion. They said, okay, can you just show us what's flying around? Can you make a graph or something? So we said, I'm the business guy, so I was like, well, maybe there's something here, so maybe we can make profit out of it, and maybe we can generate revenues, make product market fit. But we were just very early on in a very faulty system. So we just started to count adults flying around. Well, we had one camera on 2-3 hectares, so we were already a little bit surprised this is never going to work. But it did, because every time, again and again, we had these growers where we saw this moth flying sometimes up to 6 weeks earlier than the conventional traps. Well, if you think about 6 weeks in the insect lifetime, that is a lot. For moth, it's about one generation that you just completely miss. And it makes sense, because in the beginning, there's just a few. There's some caterpillars maybe here and there. They're green, on green, so it's really hard to find. But at some point, that goes sideways. So we had a solution suddenly that in flowers where we said, hey, this works pretty nice. This is something they can use in knowing if the pest is present early in the season and how it's developing. Of course, at some point, we're like, well, this moth is not only a problem in the flowers, we also know that's a problem in tomato, very big crop, in bell pepper, cucumber, also very big crops. Can we try it out in different greenhouses? And you just try to look for those innovative growers that know that they have to make steps in the monitoring of pests. So we ended up in tomato greenhouses, and we started all kinds of measurements. And you have to imagine like this, you think, yeah, okay, you just see a white blob. How do you know what you're looking at? But actually, it's also not that difficult. Of course, we can never be 100% sure, but you can be quite sure, because you know in which geography you are, you know in which crop you are, so you can single out a lot of things, you can narrow it down. And then you start measuring all kinds of things, because in the flowers they also said, yeah, very nice, you can monitor moth now, thanks for the data, but we have 2 species. Okay, how are we going to solve this? Well, it's this one and this one. Hey, they differ in size. We have a 3D camera, so we know we can measure size. So we started to look at size, we started to look at flight behavior, so how are they moving around, how fast, etc. Wing beat even sometimes for the bigger moth. So we could use all these variables to actually make insect profiles and determine what we're looking at. And well, with data, it's also not that for insects you don't really need it real time, but if you have that on a daily basis, that's already bringing a lot of value. One more example of moth flying around, but I think you get the picture. Of course, in the beginning, you're yeah, let's say you learn a few things. You know the pest is present, okay? That's already valuable, but okay, what's for the rest through the season? We also learned that some moths prefer to fly just 2 hours after darkness and then just quit flying. But there were also moths, we learned, that fly after midnight. Okay, sometimes growers can actually use those specific things, the specific nature of those insects in their advantage. When they do a treatment for a moth, they can actually say, okay, I'm not going to do it at 5 on Friday afternoon when everybody's at the greenhouse. I have to do it at 2 in the night. Okay, that's not my favorite time to work, but I can get the best results, so it's worth it. So they started to learn from those insect behaviors. Now that we have 3 years of data, we also see that we're getting more and more from that data. Let's say your filtering becomes better and better. In the beginning, you have quite some anomalies, things that are not moth, that you count as moth, false positive, etc. All kinds of other things moving around, from cat to chicken to spiders messing up with the data, people. All kinds of crazy stuff happen, but yeah, you get better and better. And then what you start to see at some point, and we see that more and more, from flowers to vegetables, it's all the same, kind of, depending, of course, on the circumstance in the greenhouse. So I want to show one example, which is really cool. Not for the grower, actually, because he had a 10% flower loss due to caterpillars in the year 2022. But it shows the power of the data. What you see here is 5 generations, roughly. I mean, in the beginning, it's really hard to talk about generation, but at some point, you see that the population or the generations are converging to the same stage in the life cycle, roughly. So what we see is waves of adults. Well, the life cycle is pretty easy. Okay, it's chicken egg, of course, but you have the moth, then you have the egg, then you have the caterpillar, then you have the pupae, and then you get the next moth generation. We are only seeing moth, so keep that in mind. But every time, it's about 4 or 5 weeks, depending a little bit in the season here in August in 2022. Here, the problem actually is happening for the grower, but the problem is starting much, much earlier. So remember that here we see, it's a sample that you take actually of a few hectares with a few cameras. We have 5 collars and 5 cameras here measuring adult flights. But you see something is happening here. So remember here that we see at the peak 600 moths passing 5 systems, so about, more than 100 a camera a night. If you go to the first part, we zoom in, you see that in the 3rd generation, roughly, we see about 20. So in 10 weeks' time, the population goes times 20. Well, that is something which is very interesting, but moreover, you want to prevent, because that also means 20 times as much caterpillars that are eating away your flower heads. But before that, it even starts. So what we know and experience with growers is that these 2 generations, and it's not really sure if you can talk about generations, but here it starts. And this is completely missed today. But if you can do something here, you can prevent that from happening. And that's also relating, of course, to the drone case that we were building. You want to maybe fly a few times a night, 0 to 5 times in the beginning, rather than flying 620 times, because that's where you can stop it. And of course, we're taking a sample, but it's also strange that in a 2.5 hectare greenhouse, that with 1 camera, we see so much activity that we know that they're so active in the greenhouse, so mobile, that you will get, with some assumptions, you get enough attempts to kill them in the early stage. I mean, a moth lives about 10 to 15 days, depending on the pest, so you have some time to intervene before it comes to full, if it's a female, a full 300 eggs that they deposit. It takes some time because they need to mate, they need to get, let's say, mature kind of. There is some time to intervene. So you see that this pest monitoring is really, really helping growers. And what we see with some growers is that, especially, for example, this grower, they said, okay, we had this data. This was a learning year. Okay, we had quite some damage. They did the normal thing. In 2023, of course, there's a lot of other things happening. How much influx do you have? What's the climate in general? Warm winter, cold winter, etc. But in 2023, they got smoothly through. They had 0 damages. They had one time of influx, but they were just really short on the data. We saw something happening, they intervened. And that doesn't mean that they're just using biological control like natural predators, but they're using definitely much less. And that's already saving them on using, that's already saving pesticides, time, but moreover damage. And that, of course, all goes hands in hand, because, a lot of damage, triggers a reaction of kind of panic, risk, that they want to act on. So we have this monitoring thing, but of course you get into situations where growers say, yeah, moth is a problem, but it's not my top 3 issue. Can you also help us with other pests? Yeah, but it's really hard with what we are building. So at some point, maybe you're familiar with it, BioBest approached us. It's a provider of biological control and pollination, for example, in some bumblebees for tomato. And they said, yeah, you have these big insects, it's very nice, and we are developing some customers together. Can you also look at the smaller insects? So we thought, yeah, but they're already doing that. They have these sticky traps, maybe you're familiar with it, where the insects are attracted to. Once a week, someone goes through the tomato crops, and they start to count 20 of these sticky traps with very tiny spots on it and discriminate insects, put it in an Excel sheet, and start to look what's happening. Okay, that's very laborious, and you often miss the real hotspot because, yeah, it's a balance between time and outcome, kind of. What does it bring? And we thought, yeah, how are we going to do this? I mean, they thought, yeah, can you maybe use your drone and scan those sticky cards in the greenhouse, or can you use the existing camera with a sticky trap? Yeah, but that's not the perfect sample for these insects. Compared to moth, which are very mobile and spread well through the greenhouse, they're very local hotspots that develop and needs to be seen in time to prevent further outbreaks, the ripple effect. So at some point we thought, okay, you already have an AI, a solution to take a picture with your phone from the sticky card, discriminate the insects and count, so that's already moving in the right direction, but it still costs a lot of time. You need a good phone, good camera, the lighting circumstances is quite difficult. So we devised a solution which we call TrapEye to take this image out of the greenhouse automatically. So the AI is still in the cloud, but those pictures are taken from the field automatically and brought as data to the grower. So that saves them a lot of time. And rather than people going through the crops, collecting all the data and accounts, they just sit behind a desktop kind of, with a working laptop with no updates. They start to see what's happening with all the pests, and they can act on that. And they can really look for the hotspots and intervene there, which enables, of course, spot spraying, or even better, application of biological control on those spots where it's most needed, rather than just, we're going to do the whole treatment for the whole greenhouse. So you have to imagine such a system where we put 40 a hectare, so 1 per 250 square meters, which is much more than the other cameras, that are just collecting this data, these pictures, every day at a standard timing, and just start to count the whiteflies, the thrips, the leaf miners, whatever pest you can have in the greenhouse. Just giving them heat maps and insights from day-to-day basis. Now, that data, of course, is one. But we already see with the moth data, with the whitefly data, that you can kind of predict what's happening. And that is relevant. So maybe not in the long term per se, because it has to do with a lot of climate and other variables, but in the short term you can. And we see that with the moth we can say, okay, based on the adult activity, we can validate with growers, with consultants, with researchers, when, for example, the damage happens. So we see time and time again that from let's say, an increase of a pest, we can determine when the eggs will be deposited or when the caterpillars will hatch. That's very important if you're thinking about biological control, because in the past you just sprayed something and you didn't see any living being for 3 months, to say it a little bit exaggerated. Now the timing is everything. I mean, you can, let's say, control a caterpillar with something that's a parasitic wasp, but if the wasp is already, or a bacteria, but if it's already too big, the caterpillar, it will just defend itself and survive. So you have to be in the first 3 days of the caterpillar, for example, to actually control it. So the timing, we are now enabling growers. And we do this regularly with growers, and then we evaluate. Sometimes they call me, hey, I see this and this happening. When do we expect the caterpillars? Well, 8 to 10 days, and then they call me back, yeah, it was 7. So they also start to learn. So they are now the AI in themselves, kind of, to react to it, to make with their experiences and everything they have. But more and more we are trying to put it in models, getting to models where we can just give them decision support. Rather than just guessing or doing weekly sprayings, we can now start moving to moments that we say, this is the right moment to treat pest A, B, C in this life cycle stage. And then, of course, it's still very complex because we're not people that do something about real crop protection with chemicals or biological control. And there's a lot of regulations. You can use this in tomato in the Netherlands, but not in Belgium. But what you use in tomato, you cannot at the same time use in flour. So that's constantly changing, of course. So we really need to collaborate with people in the field. Yes, we are a tech provider. We can give insights, but at some point it stops. You need researchers. You need providers of control. You need the grower. You need people that are enthusiastic about this, because yeah, that's also, of course, something very, very important. And that's the way how we collaborate, constantly looking for those kinds of partnerships that we can work together in this integrated pest management principle to really make the move from biology and chemicals to biology and technology, because we know that we can enhance biology with just the right information for growers to act on. Now, you see that we talked a lot about, we started with drones, we talked a lot about monitoring. I think that's also the stage where most companies are, but we are not stopping at the control. We see that from all the data that we gather, if it's live or real time or not, we are learning things that we can use in our advantage. So we're constantly looking, because based on the triggers or the reactions or the patterns that they have, what in nature can we use to control those insects. And some things I cannot tell because it's public, and IP that still needs to be protected. But we found some things that are such a hard trigger for certain insects that they don't want to be in the area anymore that we treat. We're not killing them, we're just scaring them away, kind of. We see sometimes with some pests overnight, 99% reduction in flight activity. Okay, they're not killed, but we're still investigating where they went. But they're not there anymore, and they're not there spreading eggs. So that is very cool, because if you can do that, you can keep a certain surface completely free from a pest being there without doing an actual intervention on your crop with your people or whatever. Yeah, I hope in 1 year we can share a lot about this, because there's quite some experiments going on, but that's really cool. No flying is no distribution, and we just stop them from spreading around. I hope that I gave a little bit, I mean, it's very practical, and we're a commercial company, so sometimes it may be hard to relate to research, but you can imagine what kind of, yeah, we're opening kind of a box of Pandora. I mean, we're now collecting a lot of data. We're seeing that we can make some estimations together with the grower from our experience and their experience, but this data is going to help a big deal in applying new solutions and biological control effectively, and we're really excited about it, obviously. So if you are as excited as me and you're really into pest control, I think in horticulture, but of course you can imagine this in agriculture, then I'm happy to chat, of course, and think about potential possibilities in the future. Thank you for your time.
Thank you very much. So, questions from the audience? Well, okay, we have one question.
Thank you very much. Very nice speech. And a question. In your opinion, it's possible to apply your techniques also for the monitoring of processionaria?
For what?
Processionaria, I don't know, maybe my colleagues can...
It's a moth kind of butterfly. Well, the cool thing is that we see a lot of moths flying around. So how we typically do it, I mean, we have some target pests. So the Chrysodixus is a big problem, like I showed. The Tuta absoluta, that is in tomato thing. There are quite some other moths. But typically, if you go into a greenhouse, you have, in a crop, you have one, sometimes two moths. So what we just go in there and start validating with the grower. Okay, we see this? Do you actually see something happening after that? Okay, then we know we're right, and we start to filter into the data and make it a model. It takes some time, but sometimes it goes very fast, sometimes a few months, and you're ready. So eventually, I think, yes, if it's flying at night, what we're currently focusing on, yes, that will work.
Okay, thank you so much. Because in Calabria, we have a huge problem with the processionaria, but it's, okay, it's in the forest, but maybe you can tune it, because I think that they will spend a lot of money about it.
And they fly inside the greenhouse, or is it outside?
No, it's, the problem is that these are outside, into the forest. Okay. But they are destroying a lot of coniferae. Okay. So it should be something that you are interested in.
Yeah, maybe we can share some information after the presentation.
Okay, other question? Congratulations for your idea and for your presentation. I would like to ask you something about what's happened when your system is in front of an insect more than 5 millimeters, but are not pests. And I think for the useful insect.
Yeah. It's a good question. So the system is constantly evaluating everything in the view. I mean, for the monitoring, you can take a little bit more time because you process it in the morning and then you present to the grower early in the morning and they're happy. But for the control, you have to make real-time decisions. So the system is able to track more insects at the same time. Sometimes we see 20 in certain circumstances. And you can tell the drone to just focus on certain, let's say, certain species. So if there is an insect in flight that we do not want to catch, yeah, we're not going after it. The system is not triggered. Yeah, we just single those out that are triggered. But I think you mean that accidentally passes by. Yeah, that's a good one. It doesn't really happen that often because, I mean, yeah, we sometimes see 20 insects in scope at the same time, but that's very rarely. So there are a lot of insects, but there are also not that many in the end that you constantly have in view because of the nature of most insects that are, let's say bumblebees, that's easy for us because they fly different, but they fly on the day. So you have like, you can separate it. But yeah, the other insects that are relatively so small, never really visible, so it can be that we have some collateral damage, so to say, but it's not that we are, let's say, mass eliminating beneficials, for example. But I think it's a very slim chance that happens.
Okay, so thank you again, and we can move to the next speaker. Yeah, round of applause for the speaker, and I invite Matej Karasek, and so Dr. Matej Karasek is the founder and director of Flapper Drones. It's a Czech-based startup that develops bio-inspired drones. So now we see how the biological world is inspiring the robot world. And his company spun out at Delft University of Technology, where he worked as a postdoctoral researcher. And you're ready? Okay. I think he's muted. I get it from there to join. Okay, Matej, the floor is yours.
Okay, hello everyone. Good afternoon. Thanks for the introduction. Thanks for inviting me here. So the title of this section is Robots for Insects, though the last talk may have been more like robots against insects. And now it's going to be the part insects for robots. So we're designing robots that actually take inspiration from flying insects, and we design them so that they fly in a similar way. I'm from a startup, Flapper Drones, which also started in Delft as a spin-off of TU Delft. But I also spent my PhD here at ULB, and then as a postdoc at TU Delft, so I'm going to also show some of the results from the research I did over there. Shortly about us, we're a startup company, spin-off of TU Delft, already said that. We started in the Netherlands, but moved in 2022 to the Czech Republic, which is my home country. So we operate from there. And I'll start with a little demo, because probably you have not seen a drone like this flying before, or maybe not live at least. It's insects-inspired. It's not insect-like. It's not at the scale of an insect, obviously. But anyway, it can take off vertically. It can hover. I'm not doing anything. I just have to control the throttle. And I can just fly it around. It can go forward, backward. sideways. It can be quite agile actually, but the space here is a bit limited. So, and yeah, it can do circles. I'm also going to show it in front of the camera so that the online viewers see something. And what I'm going to demonstrate, it's a very safe robot, so it's lightweight. I can also touch it. It's not going to hurt me. I can put my hand in between the wings, and it keeps flying. I can push it. It holds position quite well. So that was the demo. Thank you. So you can see some specs behind me. Yeah, I'm going to talk now more about how we design these robots and also where we see the application of these robots now and in future. And so partly it will be also about use in agriculture. So clearly we take inspiration from nature. Everything that can do powered flight in nature uses wings, flaps wings, birds, insects. Yeah, I have to stay here, sorry. And while birds, they actually need to keep flying forward because they generate lift like an airplane. So they need air that is moving around the wing such that they produce lift. The smaller animals, they can actually support their weight just by flapping their wings horizontally and pushing air downwards. For bigger animals, this costs too much energy, so they can do it only for a couple of seconds. But for small animals, you will actually get like a little vortex that forms next to the wing that is stable, at least throughout the wing beat. And this creates a suction region and improves the lift production, and so you can hover. So in the past, you may have heard that bumblebees cannot fly, according to like the traditional airspace formulas, but they can thanks to this vortex. And there's this scale, so the animals that can hover are only like insects, hummingbirds, so only at a certain scale, and the physics and the scaling numbers are such that we can do this type of flight. So this also limits the size of the drones we can make. We cannot go much bigger, but we can go smaller than this. So how do you control such flight? Well, all you have as an insect are the wings, so you have to generate moments that are going to rotate your body with the help of the wings. So for example, if you want to rotate like this to fly sideways, you're just going to increase the amplitude of one of your wings, or you can adjust also the angles of the wings just to create more lift on one of the wings than on the other one. And then actually to fly sideways, you're going to do it like a helicopter. This is a wasp that is flying sideways. You can see it's going to roll, and then it moves in that direction. So it's basically, yeah, helicopter model. This is how it's called in biology also. And similarly, if you want to fly forward, you have to pitch, and you can pitch, for example, by moving your wings behind your body. The thrust vector is going to push you like this, and you fly forward. And yeah, you can also have some difference in drag in the individual wings to do yawing. In the robot, you have to be able to do all these three moments and needs to be decoupled. And we also need a simple solution, lightweight, and that's kind of the challenge. How can you integrate it into the robot? Last thing, insects, they are actually unstable if they wouldn't have sensors. So they have sensors that are helping them to sense their body rotations. They have, some insects have these halteres, which basically work like gyroscopes we have in our phones or in our drones. The same principle. Some insects don't have them, but then they have visual sensors that are fast that do that. And well, there are some experiments that biologists do where they clip off these halteres and then they can show that, oh, the fly cannot fly. Well, I don't know if that's a proof, because if someone would poke my eyes, probably I would also behave strangely, but still, it's some sort of demonstration that they are important for them. So I already spoke about the challenges when we built drones, and many of them are similar to old drones, not to flapping wing drones, but because we have to stay small and lightweight, finding simple solutions is the key. What we deal with more than with conventional drones is vibrations. So the wings, they flap back and forth. The forces are always pulsating. With your accelerometers, you're going to measure plus minus 5G easily. So it's harder to work with those signals as well. You will need some mechanism to move your wings. In order to fly for at least a couple of minutes, the only actuator we can use is a motor, rotating motor. So you need some gearbox, some transmission mechanism, but you only need 1 degree of freedom that you drive in order to get this quite complex wing motion, because you can do the rest passively. So you can see we have a wing that is slightly slack, and it's going to form the camber as it moves thanks to the aerodynamic pressure, and it then looks similar to the hummingbird on the right. And you might even see some out-of-plane motion, which actually can help, and this is again a passive effect, but you can tune your system, the stiffness is such that you get this, and it helps with power efficiency. Speaking of power efficiency, well, okay, you will typically optimize the system by running a lot of experiments, exploring parameter spaces, because the aerodynamic models we have are just not good enough, or it takes too much time to implement them. So this is just quicker. But speaking of power efficiency, this is actually a study done at TU Delft, where they flew one of our earlier prototypes in front of a fan system, so you can study the power requirements at different wind speeds. And well, for comparison, we have a small quadcopter here, and you can notice two things. While for a quadcopter, the power required to hover is or to fly is roughly constant with speed. For the flapping wing, it actually goes down. It's up to 20% lower at certain speed. So you are more efficient in forward flight. But even if we look at the absolute value, it is actually, so this figure represents how many grams you can lift with 1 watt of power from your battery. And even this metric is actually pretty good. Of course, the bigger drone, you might get higher numbers as well, but for this small quadcopter, it was about 4.5, while for the flapping wing it was 6, over 6. So in terms of power efficiency, we're at least on par with comparable quadcopters, and we know there's still room for improvement. Okay, you have to control the flight. Well, the easiest option is just to attach a tail like on an airplane. That will make you stable, but that also means you're going to lose a lot of agility. So that's not what we want. But this is how the project in Delft started. One particular thing you can notice is that we didn't use 1 wing or 1 pair of wings, but 2 wings that are flapping like that. And there were 2 reasons. One is, like this, you eliminate a little bit of the rocking motion you would get otherwise, because if you have the wings moving like this, your body's going to move in the opposite direction. If you have a pair of wings, this gets canceled. And the second reason is that the wings, as they interact, this actually improves the efficiency. And you can see that even in animals, because when they try to get maximum thrust, they're going to enlarge the amplitude of their flapping, and they're going to start hitting their wings. And this is, some people believe this also improves the efficiency. So what is inside this particular drone? We actually have 2 mechanisms, each driving individual wings. So there's like a linkage mechanism that makes sure the rotation of the motor is transported into flapping. These are independent, so we can fly sideways by that. The 2 gearboxes can be moved like that, so this is what we use to fly forward, backward, and then there is a third actuator at the bottom that is tilting the roots of the wings in a way that we can yaw. So it's 3 quite separate mechanisms that we combined, but that makes it quite robust and, as you could see, quite agile. We also use this in an earlier prototype we made still at the university that was even smaller and lighter. You can see that actually was even more agile because the inertia is smaller, so you can do these sort of flips. And there are also other ways how to do it. I'm not going to go into the details, but you can think of mechanisms where you can control the amplitude of the individual wings or where they move with respect to the body, just by adjusting. So we use some 4-bar mechanisms here, and we found a way how to adjust the kinematics of that 4-bar mechanism with servos to achieve that. That was for Hummingbird robot here at Ulbe. You can also do that by using a wing that is going to give you more thrust if you make it less slack and less wing if you make it more slack, less lift, more lift, I wanted to say. And if you, so this doesn't have 3 wings, but it's a wing shown in 3 different positions. If you make it more slack, for example, on one side and on the other side with some servos, you're going to generate roll moment. So again, you can use this to control the flight. This is the Calabria robot made here at Ulbe. Emanuele is also involved in that. Otherwise, it's research at the lab of Professor Premont. And you can see that you can also do it this way. It's one of the only in the world that can fly like this. Okay, so in terms of sizes, we can build them from about 60 centimeters. Maybe we can go bigger. We can go much smaller. But there's a limit between what we can do with a battery on board and be free flying. If you want to go smaller than that, there are people that demonstrated you can fly at really insect scale with a robot, but then you need to use piezo actuators, and typically you need off-board power to fly because you cannot integrate everything into such a small package. But it's just a matter of time until we have better actuators, better batteries. We'll be able to do that. The physics of, at least the aerodynamics, allows us to go smaller. Okay, so why are we doing all this, right? You must be asking. Initially, when it started as a university project, it was just pure curiosity. Can we make a machine that flies like an insect, like a hummingbird? But we actually demonstrated, well, it can, and actually flies pretty well. It has some advantages. And these are them. I already demonstrated that I can, when it's in flight, I can touch the wings. It's not going to hurt me. It's not going to cut me like a propeller would. And at the same time, the drone keeps flying. If you do that with a propeller, you're going to get cut, and the drone's going to go down. Of course, you can design some protection around it. That means extra weight. That means the drone is going to be heavier. It's going to be louder. So you don't want that. This basically solves that. The sound is different. I don't want to say it's less loud. The sound intensity levels are comparable. But the frequency content is different, and for many people this is more acceptable than like the high-pitched buzzing. And it also looks kind of friendly because it has these wings. So we think this combined makes it ideal for applications where you want to fly close to people. You have a safe drone that is not so intrusive. And in terms of sound, we actually know we can do better because a lot of the noise comes from the gearboxes, and we can work on that. With a propeller, the sound or noise comes from the aerodynamics, and you will have to make trade-offs if you want a less loud propeller. Now, in the context of agriculture, we did actually some tests when we were still in Delft in the greenhouses of Wageningen University. And you can see what happens, for example, if you fly into leaves of a plant. I think this is eggplant greenhouse. We compare it to quadcopter of the roughly same weight, so it's about 100 grams. So you can see that the flapping wings, they just tolerate the leaves, and they don't cause much damage to them, if any, while the quadcopter will cut through the leaves, and once it hits a bigger leaf, which stops its propeller, it just crashes. Similarly, if you fly into a flower, like a gerbera here, again, no problem with the flapping flyer. While here, if you notice, it's just going to chop off a couple of the plants, flowers, and it's going to crash because once the propeller stops, you go down. Again, there are some control strategies how you can avoid that, but it's harder for the propeller-based drone. And finally, wires. If you've been to a high-wire greenhouse, you know they are everywhere. They are quite hard to see, well, especially on this poor exposure with this projector here, but even for computer vision, it would be quite a challenge to detect them properly, so you may bump into them once in a while. And this is really like something that kills the propeller-based drones. It just goes down immediately. Again, here, even if you try to kind of go there sideways, it can get stuck in it, but it keeps flying and you can always recover the drone. So what would be the possible tasks? flapping wing drones could do in horticulture. We cannot carry heavy objects. The payload capacity of this one is about 30 grams, so about 1/3 of its weight. But it can be a sensor, so you can measure all sorts of things. We don't know that much about horticulture, but maybe you have ideas what it could carry. We thought of temperature, humidity, air quality, but it could be some sort of artificial nose, so it could measure either sense diseases or ripeness of the fruit maybe. It could collect images, but that's a challenging one with this drone because it shakes more, it vibrates more than conventional drones. But there are applications, well, we heard about exterminating pests, but maybe just carrying them off. I got a farmer from Estonia, I think, a greenhouse farmer from Estonia reached out to me and said, hey, we have this problem, so we get birds that fly into our greenhouse once in a while, and then they poop over our product. And we don't want that, of course, because it's herbs that go into a supermarket, and we cannot have poop on that. And could we use your drone to chase them off? And we know that animals, they're smart, so they will learn that, okay, this is maybe not going to work. But if you have a drone that flaps its wings, they're much more serious about it because it looks more like they're real predators in nature. And finally, pollination. Of course, this is the hardest task, I think, especially if you have to go like to individual flowers. But if you have to go to individual flowers, it's very likely you're going to have to interact with the leaves and everything. And I think, you know, like natural flowers, they kind of evolved around plants. So this is, I think, the best design if you want to fly next to leaves. But you might have some other ideas as well. We are actually just developing these platforms. We sell it as a developmental platform. People can do all sorts of things with it. But we see this as a potential future field of application, and we're involved as an industrial partner in a project led by, in Holland, in Delft and TU Delft, but there are some other companies, including Pest there as well. And yeah, the developmental platform, as we sell it, it's actually an open platform. So you buy the hardware, but we use open source tools so that you can do all sorts of things with it. It's sort of a flying Arduino. We use flight controls from BitCraze, which are very easy to work with and very popular in research. And it allows you also to operate multiple with some other software tools, multiple units at a time from a computer. So we usually sell it for research and development, as an educational tool, and we also see a lot of interest and a lot of potential in entertainment sector. So we can decorate these, light them up, fly them in informations. The theme was robots for insects, insects for robots, and I want to show that here we actually can do both because we used one of these robots to learn about natural flyers, because we could use it as a sort of model of a fruit fly and learn more about the dynamics. Why? Because typically research on insect flight is you're going to record and you're going to analyze the footage. But here we can do that, but we also know the internal states of the robot. We know what it was doing intentionally and what was some passive effect. So you can learn from that. So you can actually do high impact research with these robots. And there is another example that was published in Nature from TU Delft, where they put an artificial compound eye on it, and they could show, you can estimate attitude using optic flow from this sensor. Okay, entertainment, just to entertain you towards the end of the talk. We do a lot of things like this small shows. This is actually flown manually. It's not scientifically interesting, but it's, I think, beautiful. But we can also make these pre-programmed. And this is sort of a testing ground for us for later, more serious industrial applications. So we can control them within some positioning system in a synchronized way. It shows we can operate multiple units at a time. We can master their control quite well. And yeah, you could just take the system, put it in a greenhouse, put a sensor on it, and fly around. Of course, the battery is going to get depleted within 5 minutes. So right now, you just have to stop, put a new battery in. But yeah, you need to develop charging systems, etc. So it's a long way, but that's why we start with this, where it's not so important to have 24/7 operation. Okay, finally, some overview of the applications we see for this type of drones in future. So, like entertainment, maybe theme parks where you have flying ferries just freely flying next to you. Also robotic guides, so anywhere where you need a flying robot and you need it to be safe, to be friendly, to be accepted by people. Then in horticulture, for example, monitoring, maybe pollination, could also be in warehouses. And one use case which might be a nice one is flight in extraterrestrial conditions, because I said we're now kind of constrained to a certain range of sizes on Earth, but if you go to a different planet or different place in the universe where the density, air density and gravity are different, you might end up with different scales of these robots. And you may have followed the Ingenuity helicopter on Mars that sadly had its last flight in, I think, last month. And the reason it stopped was it had a rough landing, crash landing, and it had a strike of its rotor with the ground. And of course, the rotor is spinning at very high speed, a lot of energy stored in there, and when you hit something, it will break. With flapping wings, you don't have this, because the wing goes back and forth, and if you touch something, it's at the point where the wing is stopped. So a damage of the wing is actually less likely than of a rotor. Okay, that was it for me. Thank you very much for your attention, and if you have some questions.
Thank you very much, and I don't know if there are questions. Yeah.
Hi, very nice piece of art.
Thank you.
I was curious, how much bigger or how much smaller could you go with the physical dimensions?
So with this particle concept, we can go about half the size, which means 1/3 of the weight. It will still fly for 5 minutes. You just reduce the payload. If we go smaller than that, we get limited by the efficiency of motors. Because if you have DC motors at certain size, they're going to lose their efficiency. And to go smaller, there are no other actuators, actually. So that's kind of the limitation now. And we hope someone's going to come up with muscle-like actuators, which would open the path to smaller drones.
Really compliments.
Thank you.
Maximum endurance with maximum payload.
So if we use the maximum payload, 30 grams. So if
30 grams.
30 grams, yes. So if that is a sensor that doesn't draw too much power, then we can fly 5 minutes at hover, more if you fly forward. If we use this payload to carry the biggest battery it can, then we can do 15 minutes at hover again. So would be a bit more in forward flight.
Thank you.
Possibility of energy harvesting from in a wireless way? It's possible.
Wireless?
In a wireless modality. I mean, with electromagnetic field and use an antenna to catch the and transform it in
it could
energy.
Be. I'm not an expert in that. I know that this is kind of being thought of. In general, like when you fly, you use quite a lot of power. So I guess to harvest enough power to fly, the sort of duty cycle would be very narrow. So you would spend a lot of time charging and then short time flying. But yeah, it could work. Realistically, I think now some sort of charging pad, dedicated charging pad for charging would be probably better because you can charge at much higher power.
How big is the battery?
So this one has a 2-cell 300 milliampere hours battery. So it's a little bit over 2 watt-hours of energy.
Okay. Thank you so much.
Related with your question, there are flexible organic photovoltaics to cover the wings. That might be interesting. But my question is going to be something else. I'm a materials scientist who are designing bio-inspired polymers, like your wings. I think it's either paper or textile-like material. So how did you come up with such a material? I mean, what is your selection criteria?
So our requirements are it needs to be lightweight, obviously, and rather stiff, or it shouldn't stretch too much. But why we use this material, which is polyethylene foam, that's because of the acoustics. So you could use some thin plastic foils, but they will typically be quite loud when you like move them around. So like Mylar and these sort of things. And the foam actually, doesn't have this signature, acoustic signature. So that's why we use that. But it's certainly not the final choice of material. We can improve there. But this is what works sufficiently well at this point.
Okay. Well, if there are no more questions, let's thank again Dr. Karasek. And then I invite the last speaker of this session, Professor Marco Dorigo. And so in the meanwhile, it's my pleasure to introduce Professor Dorigo, that is the director of the Iridia lab at ULB. And his CV is impressive, and to give some numbers, his research has been cited more than 140,000 times, and he won several prizes and directed several projects, among which an ERC Advanced Grant. And it's okay? Okay, the floor is yours. Okay.
This way?
Yes.
Okay. Okay, so I will talk today about swarm robotics, from social insects to social robots. The second part of the title was invented by my friend Emanuele. So I'm trying to put things in this context. So first thing is, what is swarm robotics? So swarm robotics is embodied swarm intelligence. So I have to explain what is swarm intelligence. Then swarm intelligence, we can see swarm intelligence as a system property that is some global behavior that is shown by a distributed system that is composed of many components that are self-organized. Typical example are social insects. So there is a connection to the title. It is also a research discipline that studies the collective behavior of decentralized self-organized systems. And these are systems that are made up of a population of agents that interact with each other locally, and with each other and with the environment locally, and that by these interactions determine an emergent or resulting behavior. So the individuals that we study in this swarm intelligence system do not have a global knowledge of the environment, so they only know about what is in their neighborhood. They interact with the other agents that are close by or the local environment, and do not, it's important, do not exploit forms of centralized or hierarchical control. So what we do is often we collaborate with biologists that do study real natural swarms, like so what you observe in ant colonies or swarm of bees and so on. They study how these swarms organize their behavior, how they do allocate tasks, how they communicate. And then we try to take inspiration from these studies to solve interesting problems. So I've been working many years in the past on trying to solve difficult optimization problems like discrete optimization, combinatorial optimization, using distributed algorithms that are inspired by the behavior of ant colonies. And more recently, which is still in the last 20 years, I've been working on the control of large numbers of swarms of robots. Okay, so as I said, swarm robotics is embodied swarm intelligence. It means that in swarm intelligence you have agents. They can be software agents. In swarm robotics, these agents are robots. And what we study is how to design and control large number of these robots. Okay? So in using self-organization, so only local interaction, as I was saying, I repeat, only with the environment and with other robots, no central control. And the main goal is to develop such systems of physical swarms that solve some interesting problems or perform interesting tasks and have properties of fault tolerance, scalability, and flexibility. The robots that we use are relatively incapable, which means that they might be sophisticated, but they are supposed not to be able to perform alone the tasks they are given. So they need to cooperate. And let me go to the next. So I already said, why do we want these swarms? It's because they are fault tolerant, so there is no single point of failure. You can imagine that having many robots, if one fails or a few of them fails, the system can continue to work. They are scalable because of the lack of central control and because of being based on self-organization. You can imagine that you can add more robots to the swarm if you want more work to be done without the need to reprogram the swarm. And since there are many, you can have many activities going on in parallel. You can have division of labor and so on. So there are a number of interesting properties. And so what we are doing in my lab is we design and implement software that control these swarms. We perform theoretical analysis of the swarm behaviors that we observe in the robots, and we develop tools for the research. So we have developed a simulator, Argos, that can simulate up to 10,000 robots in real time. We design and implement small research robots and tools to run experiments with these swarms. So if we go to the main question that I'm interested in, that is how to control such swarms. In principle, there are two extreme approaches, possible approaches. One is centralized control. Okay? So there is one robot or one external computer that knows everything about each of the robots, its position, its status, and so on, and controls them. Okay? In favor of this solution, there would be the fact that most engineering systems are controlled in this way, so we have a lot of knowledge how to program centralized systems. However, there is this single point of failure problem. It's difficult to scale, and it's not what we want to do. So the other approach is self-organization. That is where we can take inspiration from social insects. That is coherent with our goal of having a fault-tolerant, scalable, flexible system. But there is a problem that is known as a micro-macro link problem. The problem is that, in principle, we want to program the swarm but we can only program the single robot. So how do you move from programming the single robot to having a swarm do what you want? So there have been a number of, recently there have been a number of ways that have been proposed to do so, but I will present here the classical one, that is very empirical approach, where you design, implement the behaviors that you want your robots to perform, and then you test these behaviors first in simulation. So you run the system in simulation, observe what happens, and you modify the behaviors until you are happy. And then you move on to test on the real robots, and you recycle again until you are happy with the final results. And then you are done. Okay? To design these basic behaviors, these behaviors that you give to the robots, there are a few possible approaches. One is standard programming. You just know what your robot should do, and you program it. Sometimes you do use bio-inspired programming, and sometimes you can use machine learning. Okay? So today I will focus a little bit more on the bio-inspired programming because of the title, basically. So there are many different research directions I'm following in my lab that go from the collective decision, stigma-guided construction, coordination homogeneous robots, coordination of heterogeneous robots, or robot swarm security, and so on. But today I will focus on the first three, because for the first three it was pretty clear the connection with the social insects. Okay? So I will talk about collective decision robot swarms and how honeybee house hunting and ants finding a shortest path have inspired these collective decision methods that we use. How the nest building in termites have inspired what I call stigma-guided construction, and how ants finding a path between two locations, the shortest path between two locations, has helped in letting a swarm perform a coordination task in an homogeneous swarm. Okay. Okay, so as probably you know, there is this work on the waggle dance of honeybees. Okay, so when our honeybees search for a new nest, they perform the search, and then when they find a possible location, they fly back to the nest and they start advertising the position and the quality of the nest. And the amount of energy that they put in this waggle dance gives an indication both of the distance and of the quality of the nest. So it's an assessment of the possible nest for moving to. So what the honeybees are trying to do is to select the best among a certain number of possible options. And we are trying to do the same with our robots, and we want them to solve the best of n problem. That is a collective decision problem where you have a swarm with n robots that have to collectively choose among small n available options. Okay? So these options can be where to go to retrieve objects, where to aggregate, which path to choose to move from one location to another, and so on. So each of these options has a quality that is a function of a value and of a cost. The value is an internal preference of the robot, so it can give to a different option different values, and the cost is related to how much does it cost to the robot to get to choose that option. For example, it could be the distance of the resource to be collected. Okay. Then the collective decision is when one large majority of the robots has the same option, or chooses to have the same option. Okay. And the problem is solved when the collective decision is the one for the highest quality option. So I will try now to show you a short movie that presents these. I Let's see if I can manage to have the sound also for the people online.
Study collective decisions in swarms of simple robots. We take inspiration from the house hunting behavior of honeybee swarms. When house hunting, honeybees choose their new nest location in a self-organized manner. The collective choice they make is the result of simple interactions between the swarm members. In our artificial swarms, collective decisions are also the result of self-organized interactions between individuals. The kilobot is a small and cheap robot with very limited capabilities. It can move in a straight line or rotate in place around its center. The kilobot has only one sensor with which it can measure the brightness of the ambient light. It can also exchange 3-byte messages with neighboring robots, and when receiving a message, estimate the distance of the sender. We consider a site selection problem to study collective decision-making in a swarm of 100 kilobots. Robots are initially located in the nest, the area where robots exchange site preferences and take individual decisions. From the nest, robots can move either to the red or to the blue site. The goal of the swarm is to find consensus on the best site. In our case, the red site. The quality of a site is an abstract numeric value. We evaluate the noisy robot's perception of a site's quality using infrared beacons placed under the arena surface. Such beacons broadcast noisy quality values. A swarm has made a decision when, as a result of a decision-making strategy, a large majority of robots have the same preference. We control the kilobot with a finite state machine that implements our decision-making strategy. In the dissemination state, the robot is in the nest, and its primary goal is to promote its current site preference. To do so, the robot repeatedly broadcasts its preference while performing a random walk. Before moving to the exploration state, the robot collects the preferences of its neighbors. It then applies the majority rule to update its preference, which determines the site it will explore next. In the exploration state, the robot travels towards the chosen site. Once there, it randomly explores the area in order to estimate the site quality. Eventually, the robot returns to the nest and re-enters the dissemination state. In a way similar to honeybees, the effort each robot makes to promote a particular site is proportional to the quality of that site. Specifically, a robot promotes its preferred site for a time that is proportional to its current estimation of the site quality. This modulation mechanism introduces a positive feedback that over time leads the swarm to choose the highest quality site. Self-organized collective decisions let a swarm overcome the limitations of its individual robots.
Okay, so what is interesting here is that this model that we have used, that was inspired by the honeybees hunting behavior, can be generalized and be used also to solve related but different problems. So we can look at the robot swarm as an information processing system where there is some information entering the swarm and the collective decision is the output. And activities of the robot swarm that are interesting for this particular collective decision making problem are information collection, information dissemination, and how the feedback is used by the swarm and how decisions are made. Okay, so what we have seen in the video is that each robot in the swarm is controlled by a probabilistic finite system machine that switches between the dissemination state and the exploration state. And these two states are characterized. The exploration state is characterized by the fact that during exploration, the robot is estimating the option quality, and it takes some time to do so. And then, when it is in the dissemination, it has to disseminate this information that has collected during exploration. And after dissemination, it has to make a decision on what should be the next option to explore again. So, in the honeybees example that I had shown before in the video, we have seen that the information collected during the exploration, so the feedback, and that disseminated during dissemination, is a kind of direct modulation. This means that the better the quality of the explored option, the more time I spend disseminating. Okay? So I see something very nice, I spend a lot of time telling other people it is very nice. There is, however, another option that is indirect modulation, in which the dissemination, the dissemination duration is fixed by the frequency with which the opinion on the dissemination are changes as a function of the cost. So to let you see how this works, consider this other biological example. This is a very old work by Jean-Louis Denebourg of my same university, where you have some ants that are connected. Here is the nest of the ants, and there is the food source. The ants are connected to the food source by this double bridge. Okay? So in this experiment, what Jean-Louis was showing is that because of the fact that ants choose where to go as a function of the amount of pheromone that there is on the ground, the system tends to converge towards the usage of the shortest branch. Basically what happens is that at the beginning there is no pheromone on the double branch, and then ants choose randomly whether to go left or right, but those that go right are the first to arrive, and then when they go back, they find a little bit more pheromone on this branch, and this is kind of positive feedback that let the system converge toward the use of one branch. Okay, so in a similar way, even though it's only analogically similar, okay, so it's not because our robots cannot leave pheromone on the ground. So what we have done is to consider robots that have to go from a starting position, so the nest, to a goal location and go back. And in this case, the robots, well, you will see in a moment in the movie, the purple robots are those that select to go on the left, and the green robots are those that select to go on the right. Okay? Then what happens is that when they go back to the nest and they meet each other, they decide whether they should again keep their opinion, that is, I believe that purple is the shortest, or I believe that green is the shortest. And by observing, and they do so, by observing what the other robots that have in their neighborhood do. Okay? So let me show you the video. The robots start with random position, random opinions, and they start to move. So this robot is here now in the nest, and when it meets another robot, it decides with a majority rules whether to keep its opinion or not. Okay. So in this case, because the robots that choose the shortest path go back more frequently than those that choose the longest path, then they will meet each other more often, and the system converges towards the shortest path. Okay? So it's similar to the behavior of the ants, even though here the decision is made not based on the pheromones left on the ground, but on the fact that being this shorter, they meet more frequently. So also this behavior can be modeled in the same way as the other one. So we have the exploration state, and the robots collect information about the quality of their current opinion, but the modulation of this feedback, so this information, is done in an indirect way. It's not that I am going somewhere, I look how good is the option, but it's rather I go somewhere, and since it takes very short to come back, it means that the solution was good. It took very long, the solution was less good. And then they move in the dissemination state, and they disseminate for a fixed amount of time, and then they make this decision based on the majority rule. The same, again, the same model can be used to classify environments. For example, here, we consider this environment where these robots move, where the ground can be painted in black or in white, and the goal of the swarm is to understand whether there is more black or more white. And again, each robot can only see what is under its sensors on the ground. So they can have two opinions. If they are red in color, now in this picture they have no color, but you'll see in a moment in the video, they can be red or blue. When they are red, it means that their opinion is that in that moment there are more black tiles. When they are blue, their opinion is that there are more white tiles. So what they do is they go around and they sample the environment. And then after some time, they start to advertise. And they advertise for an amount of time that is proportional how often they saw, it's proportional to the percentage of time they spent over a given color. Yeah. Okay, same as before, we can model we can build a stochastic, probabilistic stochastic machine that control the robots with the exploration dissemination states, where this time, the time that the robot spend disseminating is directly proportional to the opinion. So like in the house hunting behavior. So if we run experiments, we see that even when a situation like this one, in which if you look, you cannot say whether there are more white or more black, not easily. Okay? So it's difficult. It's quite difficult problem also for the robots, but still they manage to converge on the right solution. In this case, was 52% black and 45 white. Okay, so this work has been published in a number of conferences and papers. If you, in the journals, if you're interested, and these are all the people that have been collaborating with me on this problem over the years. The second example I wanted to show you is a work that is not as much developed for the moment. So we have prepared all the tools, but we still have to get results that are publishable. So the idea is the following. We have stigmergy. That is a kind of indirect communication that happens through modification of the environment that is observed in social insects such as termites. So what stigmergy is the following. Can be explained in this way. So when the termites, for example, they start to build a nest, they start to build a nest around a queen termite, these big insects here. Okay? So this is the dimension of queen compared to a worker termite that is here. So what they do is the queen termite emits some pheromones that the working termites use as a reference to understand where the queen termite is, and they start to build pillars around the queen. These pillars are formed of small earth pellets, small quantities of earth, that they chew and in which they add pheromone. And they place these earth pellets one on top of the others so that these pillars start to grow. And then At some point, because of the pheromone emitted by the queen, so the pheromone is distributed differently or in space depending on the position of the queen, they start to, the pillars are no longer built going up, but they start to be curved to cover the queen, and they start to form arches and so on. Okay, so, but the main point is not really how this process goes on, but in the fact that there is not a plan in the termites to how to build the nest. What they are doing is basically they are applying stochastic rules and reacting to what they observe in the environment. So stigmergy, the idea of stigmergy is that the work is guided by previous work. Okay? So it's not, I do not have a plan, but I just feel something. I say, okay, someone has put there a piece of earth, I add some, and then someone else finds more, there is higher probability to add some, and so on. If you take all the termites away and you place a new set of termites, they continue to the work. It's like they were there from the very beginning. So there is really no plan. It seems there is no plan in their heads. It's just reacting to the work done previously. So what we decided to do was to try to demonstrate the use, this type of approach in a swarm of robots. So we started by building what we call sigmergic material. And we wanted this sigmergic material to be similar in some way to the earth pellets that are used by termites in construction. So what is needed is material that the robots can perceive, and this is relatively easy, and in which the robots can write some information. So the termites write information in the form of pheromones. We decided to use colors instead of pheromones, because it's easier for our robots to perceive and distinguish color rather than chemicals. So the type of object that we have built is what you see here. It's a block. It's 55 millimeter side cube. It has self-aligning magnets. It has some colored LEDs and XV communication. Okay? So it can take different colors, and the color it takes can be determined, can be either chosen by the robots that carry these objects or by other cubes that are close by. Then we built this robot that you see here, that you see here in action. That is a robot that is capable of picking up the objects and to transport them near other blocks. Okay. So the self-aligning, the magnets that we put allow the blocks to self-align, so we don't need a very precise manipulation. And then we started to run experiments to study how the robots can build structures using help from the colors of the blocks. Okay? So basically, we are trying to program the robots in a way that they can add the objects in the right place by looking at either at the shape of what has been built up to that moment or to the color of the different, I mean, something very simple, like if I see, my rule as a robot is, if I see a green object, I should put something on top, while if I see red, I should put on the right side. Okay? So for the moment, we have been able to demonstrate the construction of pretty regular structures like what you see here, but we don't have a general solution for the moment. So what we are studying now is, well, basically how to give the swarm a plan of what needs to be built in terms of the colors the robot should give to the building blocks. Okay? Another way that we are also thinking of investigating is how to let the structure direct its own construction by telling the building material what color they should take so as to guide the robots while they're building. Okay. Also in this case, there are a couple of publications, and these are the PhD students and postdocs that have been working with me on this project. So the last thing that I wanted to show, I still have some time, right? Yes. Okay, is coordination homogeneous robot swarm, where the social insect behavior that we use as a source of inspiration is ants finding a path between two locations. So in this case, the project was pretty much more general, was not specific on the particular social insect behavior. So what we had as a scenario was a search and retrieval scenario, where a swarm of robots that we call S-bots, I will show in a moment, that have, as usual, only local sensing, and that are also capable of physical interaction, so they can physically interact by attaching to each other, and are controlled by stochastic rules, how these robots can cooperate to search and retrieve an object that is placed somewhere, that is heavy, and that should be carried to some goal location. So this is the typical experimental environment. You have a room where there is an object, this one here. There are many robots, these smaller circles. There is a goal location. There might be obstacles. So in the experiments I showed today, there are no obstacles, but we run experiments also with obstacles. And where the object to be carried is heavy, so the robots need to cooperate for the transport. Okay, so in the experiments I showed, at least 3 robots should cooperate to be able to move the object. Also, the vision range of the robots is pretty limited, so they need to cooperate to find a feasible path between the goal location and the object. So this is the S-bot. It's a robot that we have built within an European project. So the main characteristic is that it has grippers and that they can attach to each other. So you will see in a moment. It has many sensor actuators, it's a camera, it's a LEDs, microphone, and so on. So we could run many different type of experiments. So here you see that the robots can attach to another robot and is strong enough to lift it. So with this type of robots, you can illustrate cooperation in many different ways. For example, here they are cooperating to move on pretty rough terrain. So they attach to each other so that this robot in the middle managed to pass over a rock. Or they can, for example, pass over a step where a single robot could not, and so on. Okay, so in order to solve the problem that I was presenting before, so the search and the retrieval, we decided to take a behavior-based approach, which means that each robot is controlled by a certain number of behaviors that are defined independent of each other, and then they are put together in a probabilistic stochastic machine. So the basic behavior that we thought were useful were self-assembly, that is capacity to attach to each other or to attach to an object, coordinated motion, that is the capacity to move in a coordinated way once they are attached to each other, cooperative transport, obvious, and goal search and path formation, as I say, to find a path from where they find the object to the place where they have to carry it. So these different behavior-based behaviors were developed using different techniques. So coordinate motion and self-assembly, we use the machine learning, cooperative transport, standard programming, and goal search and path formation. We took the BrIAS-inspired approach. So I will talk in more details only of this one, just to show you that for the coordinated motion, this is what you get. The robots are attached to each other. They're controlled by a neural network that was, whose weights were learned. Okay, similar for the self-assembling, there is a neural network that is controlling the robot, and what the robot have learned is to use colors to say, okay, when I'm red, it means please grasp me. When I'm blue, it means please stay away from me. And when I grasp something red, I become red. Okay? So in this way, they avoid to touch each other when they're blue. They are attracted by red, and after a while, they are all red and they're all attached to each other. The cooperative transport, again, this was pretty simple, and it was programmed by a student. And then the BrIAS-inspired approach. So here, the problem was to find a feasible path from the location of the object to be retrieved to the goal location. So here, we wanted to take inspiration from the ants trail formation, same as what I was showing before in the double bridge experiment, so where ants leave pheromones on the ground, and then they tend to follow the trail in probability, so that after some time they all follow the same trail. However, since as before, our robots cannot leave pheromones or other chemicals, we decided to work by analogy, and we used the robots themselves instead of pheromones. And I will explain this in a moment. So let me first say that the robots that we use have a quite limited sensing capability. They can distinguish up to 4 colors, and approximately to a distance of up to 30 centimeters. And they can estimate the relative distance of different color blobs. Okay? So in practice, what they have is a camera that points to the ceiling, but they have a spherical mirror, so they see all around. So they see other robots. They can identify other robots by blob of colors, given by the LEDs of the robots that are close by. So the BrIAS-inspired approach, as I said, was the trail formation in ants. So what we do here is the following. Imagine that this is the object to be retrieved, and this is the goal location. And these are the robots that move around randomly in the environment. And what you see here is the robot sensing distance. Okay? So the robots move around randomly in the environment, and they're given stochastic rules that say that whenever they see a given color at their sensing distance, they have a certain probability to stop and take a color that is related to what they see. So for example, here, when this robot, it sees blue, it can, with a certain probability, stop and become green, while all the other robots continue to move randomly in the environment. And then when this robot is again at its sensing distance from green, it tests with a certain probability, stops, and becomes yellow. And in this way, you can have virtual chains of robots that are built in the environment. Okay? When one robot, like this one, is last in the chain, and remains there alone for a while, okay, so there are no other robots nearby, it has a certain probability to say, okay, I give up, and the chain is destroyed. So what happens, you will see in a moment, is that there are many chains that are growing and are destroyed all the time until one of these chains happens to reach the object. Once it reaches the object, other robots can use the chain to go to the object and then to retrieve the object to the goal. So as I said, all the different behaviors are put together in a probabilistic finite state machine, and then we run experiments in simulation. So here is a typical simulation where there are 4 possible objects to be retrieved. There is a goal location, and there are these chains that are being formed and destroyed. Okay, so for example, if you focus on this one, this chain will end up being formed. And once it is formed, other robots can follow it. It has a directionality because three colors are enough to give the direction. And then the robots see the red, they grasp, and they start to pull. And where there are enough, 3 in our case, they manage to move, and then they can retrieve the object. Okay, so we can look at the experiment with the real robots. So in the video that I will show you, what you have to observe is that, first, all the robots have the same control system. But although they all have a control system, they perform different things. And in particular, they take different roles in different teams that change dynamically during the experiment. Okay? So basically, there is formation of teams of exploring robots, that are robots that explore the environment, chain robots that are chain that belong to the chain, and retrieval robots that are those that are retrieving the object. None of these robots have any idea of, explicit idea, I mean, of in which team they are, and they can move from one team to the other as the experiment goes on. So what you see here is this initial configuration of this experiment where the robots are placed randomly in the environment, object to be retrieved, goal location, and then they start to move. So you see these chains that are being built. And destroyed. Okay, so for example, that one is being destroyed. So one interesting thing is that it is quite chaotic, and it looks very much like what you, the impression that you get is the same when you look at the real ants that are doing stuff. You don't understand what each individual is exactly doing, but the work gets done. And okay, at this point, the chain has been formed, and you see the other robots are following the chain because, for example, this robot does not know that the chain is not formed yet. But then it arrives, it sees the red, grasp, and they start to retrieve. Now, while retrieving, since the sensing, as I said before, is pretty bad, they do something wrong so that they move away. But the chain is immediately repaired by another robot, and then they can start to retrieve again. Okay, so this experiment is interesting because it was the first experiment capable of showing this dynamic formation of teams in a completely self-organized way. But unfortunately, it seems that this is as complex as we have been able to go with pure self-organization. Okay? So, which does not mean that it's not possible to do more complex things. It's only that it's getting more and more difficult. So what we are doing now is I've been working in the last few years at improving the programmability of the RoboSwarm, adding self-organized mechanisms to create hierarchies or central control. So the idea is that central control, as you remember I said at the beginning, in principle is easier to control these swarms using central control. But you get into problems very fast. And self-organization is very good, but it's very difficult. It's very good because it gives you more flexibility, but it's difficult to program. So what we are trying to do is to put the two things together and let self-organization create these hierarchies and decentralized control in the swarm. Okay? So this is some work that I've been doing in the last 4 or 5 years, and Emanuele is also involved in this research, but this will be for next invitation. So I will stop here. Thanks for your attention.
Thank you very much for this very interesting talk. And there are questions? Okay.
thank you for your interesting presentation. I have a question. Each of these robots are apparently equipped with different sensors. And if any problem happens for some of these sensors, they will produce faulty information. So at the moment, are there effective techniques to prevent this from happening, because they will propagate faulty information and this will propagate across the network and will cause problems in decision making?
Okay, so this is an important question. In fact, it depends whether the faults in a robot are an issue or not. It depends very much on the task. So in some task, one robot is breaking down, okay, you forget about it and you continue. In other applications, it can be a problem. So what we have been doing also in the last 4 or 5 years is to study how we can identify these faults and how we can exclude from the swarm these faulty robots. In fact, we have taken a slightly more general approach. Instead of considering only faulty robots, we are considering what we call Byzantine robots, that our robots can be faulty or malicious. And our solution, the solution that we've been proposing, is to use blockchain technology so that we program the robots using smart contracts, and we get all the machinery of blockchain. It's not for free, but I say that can be used in our swarm, that allows us to easily detect these Byzantine behaviors and to exclude the robots from the swarm.
Thank you.
Other questions, curiosities? I would like to thank again. Sorry.
I would like to thank you very much for a very, very interesting speech. It's possible to optimize the swarm robotics for measurement purpose.
For?
Measurement purpose. I mean, to give us objective as goal to perform measurements, for example. Maybe to estimate the value of, or a 3D reconstruction, and we need to positioning the robots in the best way to achieve the better accuracy, for example.
Yeah, I guess it is possible, but it's not within let's say, the research interest that we have at the moment. We are more interested in trying to understand how to control them, to study how they can continue to work when they fail. I'm really not trying to optimize things at this stage. Okay. But yeah, it could be an interesting direction. Yeah.
Thank you so much.
Very short. So the systems you presented with the ants, and then with going from a place to another to evaluate and meeting with two opinions in the end. It seems to me they can be studied as theoretical systems, like dynamical systems with like evolutionary game theory methods. Have you looked at that at all?
It has been done. It has been done. So it was done. I didn't, because it was already done.
Okay.
Yeah, so you can study a system with differential equations. You can study, yeah, but it's not really what we have done.
Okay, so let's close this session, and let's thank again Professor Dorigo and all the speakers of this session. I let the word to Professor Garone for the final remarks.
Okay, I can use this one, it's easier. Okay, first of all, let me apologize for being late, but as you have seen, we always prefer to have interesting, we had a lot of interesting speakers, a lot of interesting questions, and it was always too cool to interrupt any one of the speakers, so I'd prefer to go a little bit later rather than missing something interesting. So let me say, first of all, thanks to a few people, and thank you first of all to all the speakers and all of you that have been with us these 2 days. Some special thanks to a series of institutions. First of all, the Brussels Institute of Advanced Studies, that is the organizer of this event, and that has allowed this event to happen. And also FARI, that has hosted here and that is co-financing this event. Let me also mention my department that has given a huge effort to make this happen. FNRS and the European Commission, in particular the Marie Curie Action, that have contributed economically to this event to happen, and to FAO that has given a technical support and a nice introduction yesterday. I also want to thank in particular my two co-chair that have worked a lot in the last 2 months to this happen, in particular Luca, that has really worked a lot. And he has helped me in finding many of the speakers. We discussed about this event for months, and it was really great to work on it. It was very fun. And also our logistics chair, it's Dr. Anja Garone, not Rossini. It was a copy-paste, and this I must correct because otherwise I will have serious problems at home. You see? Because as you will know, besides being the one who was in contact with all the speakers, in contact with everything that concerned the logistics and the communication and the technical aspects, and I don't know what else, she has moreover the hardest of the task, that is the one of being also my wife, and so having to cope with me despite my bad character, my strange ideas, my crazy ideas, and so on. So thank you very much. I also have to say this thank you, otherwise tonight at home it's a problem. And a thanks to our program committee, so Professor Frederic Francis that had to leave to catch his train and who chaired one of the sessions, Professor Raphael Junkers, Francesco Lamonaca, who has presented today, Professor Yael Edan, who has given a talk yesterday, Professor Mario Contarini, that has also presented today and that had to leave to catch his train too, and Dr. Karl Morch, that is in multiple roles. I have to thank him because I have to thank him as program committee member, as co-director of BrIAS and co-director of FARI. I'd like to say, do you have something else that I forgot? Okay, that's great. I have also two people, actually three, that I have to thank in a very, very special way. First of all, Andres, so Andres Coturruelo. So also Andres is here in multiple tasks, so he is a brilliant postdoc and a brilliant researcher who works here at FARI in my department, who is a BrIAS junior fellow and who has worked very much in the last, you have seen the last 2 days. In reality, it's 1 week that he's spending, I don't know how many hours. If we count the hours, I don't know how many weeks of vacation you have to take after this. Yes, you should take them. I'm really thankful for all your very good work. Second, very, 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 very special person, and that every single time that we organize something, we wouldn't know how to do without her, and we wouldn't know how to do without her in our department, now even at BrIAS, and I don't know in how many other places. Pascal Latouers, who has really multiple roles. You don't see her very often around, but she's really vital for all of this to work. I didn't put a photo of Carl, so now I wanted to put it here. And there are a series of other thanks that are in order. So the BrIAS directors, Frank de Koning and Serge Aumont, and the other program directors, Bram van der Boer and Anne Jacobs. All the BrIAS junior fellows that I've not mentioned yet, so Fatma, Michelle, and Shirley, who came here earlier, were helping us to set everything, and every single time help us for these BrIAS events. The personnel of FARI that had to cope with our invasion and was always very kind and smiling, even if maybe not always we deserved it. Speak for myself, of course. Finally, I want to also thank very much the personnel of FAO, in particular Rashad Al-Kafaji, the director of the liaison office with the European Union, and Margot Van Eck, with whom we spent, I don't know, many calls to try to make this collaboration with the FAO happen. I also want to thank the BrIAS fellows that are being with us for this season. Each one of them is staying with us for from 1 month to 3 or 4 months, and some even more, we hope. And it's being a great opportunity. So we are almost, I promise, the last 2 slides, and then this forum, it's over. The question of this forum was robotics in agriculture, where we are going. And one possible answer is maybe we could think to follow up with this event. So we had some crazy idea of maybe this could be the basis for a contributed volume, a special issue, we don't know, some sort of publication. Or maybe we could think to a follow-up next year. Next year, we are still in the process of understanding what will happen, but it is possible that we will have the possibility to have a follow-up. Or, well, there is a novelty coming that is starting from June. The Brussels Institute of Advanced Studies will have its own physical place, and this will allow us to do even more things. We will have 19 apartments. We will have our own seminar room, our own lounge room, our own working space room, and we can think to organize activities associated to it. Maybe, for instance, some summer school, if someone is crazy enough to join us in such a kind of experience, or maybe some week or weekend Schlussdagstuhl style. It means we kidnap some of you, we stay there for 1 week, and we force ourselves to have good ideas, to write some project, to write new research, and to do something new. That's something that in certain communities seems to work very well, then why not? Of course, join research activities. You all have my number, you all have my email. You have just to drop me a line, and I'm pretty sure that the Brussels Institute of Advanced Studies will be more than happy to foster activities like that. And if you want to collaborate in any way with the Brussels Institute of Advanced Studies, just contact us. So with this, I close here. Robotics in agriculture, where we are going. Well, I would say we are going first for a weekend to rest a little bit, and then back to work. Thank you. Have a good evening.